Have you ever looked up at the night sky and wondered about the dangers hiding in space? What scary secrets does the universe hold waiting to be discovered? What happens when the unknown and unpredictable collide with our small, fragile world? Join us as we explore these questions and uncover the most terrifying things in space. If a black hole began drifting towards our solar system, the event would unfold over an astronomical timescale, starting with subtle gravitational effects that would eventually grow more dramatic. Initially, scientists would detect deviations in the orbits of distant objects, like the Oort cloud's icy bodies, whose paths might begin to shift due to the black hole's intense gravitational pull. As it drew closer, these gravitational perturbations would extend to the furthest planets, causing measurable distortions in their orbits. The immense gravity of a black hole, which can be tens to billions of times more massive than our Sun, would start to disrupt the delicate gravitational balance of our solar system. As the black hole approached even nearer, the effects would become more pronounced and catastrophic. The orbits of planets might become increasingly elliptical or chaotic, resulting in significant climatic and tidal shifts on Earth. If the black hole came close enough, it could start stripping away the outer planets from their orbits and flinging them into interstellar space, or pulling them into its own gravitational grasp. Closer entities, including Earth, could experience severe tidal forces, potentially stretching the planet and causing widespread geological upheaval. If our Sun were to fall victim to the black hole, it might be torn apart, its material accreting around the black hole and emitting immense radiation. For humanity, this would spell the end of our solar system as we know it, marking a dramatic and nearly unfathomable close to our cosmic neighborhood. A black hole can completely destroy a star through a process called tidal disruption. When a star ventures too close to a black hole, it enters the tidal radius where the black hole's gravitational forces exert an extreme differential pull on the star. This means that the side of the star nearer to the black hole experiences significantly stronger gravitational forces than the side that is farther away. This difference in gravitational forces can literally stretch the star, a phenomenon known as spaghettification. As the star is pulled apart, its matter gets elongated into a long, thin stream of gas. Eventually, this stretched material spirals into the black hole, forming an accretion disk. This disk is immensely hot, as the gravitational energy of the infalling material is converted into heat and light. Consequently, the surroundings of the black hole can emit colossal amounts of radiation, which might be observed as a flare of X-rays or other high-energy radiation from Earth. This entire destructive process can happen quite rapidly, in astronomical terms, often over the course of weeks to months. The outcome is a star entirely consumed or transformed into a diffuse gas, swirling into the black hole, leaving no trace of its past existence. This dramatic event effectively signifies the complete obliteration of a star, leaving only the implacable maw of the black hole behind. The chances of Earth encountering a rogue black hole are remarkably slim, but not entirely impossible. Rogue black holes, which are black holes that have been ejected from their home galaxies or are freely wandering through space, do exist, but space is incredibly vast. Estimates suggest there may be millions of black holes in our Milky Way galaxy alone, yet the actual space these objects occupy pales in comparison to the expansive voids of the galaxy. The closest known black hole, V616 Monocerotis or V616 Mon, is about 3,000 light-years away from us, giving a sense of how relatively rare encounters would be. Even though black holes are elusive due to their invisibility, they don't emit light and can only be detected by their gravitational effects. The distances involved provide a substantial buffer. For instance, the chances of a star passing within 1 light-year of Earth are astronomically small. Adding to that, black holes are far less common than stars, reducing the probability even further. It would take tens of millions of years, if not longer, for a rogue black hole to wander close enough to Earth to pose a threat. Consequently, while the concept captivates science fiction writers and cosmology enthusiasts alike, current astronomical data suggests that Earth is safe from such a direct encounter for the foreseeable future. Spaghettification is a particularly vivid term used to describe what happens to objects and even people when they fall into a black hole. The phenomenon is rooted in the intense gravitational forces at work near black holes, particularly the difference in gravitational pull experienced by the parts of an object closer to the black hole compared to those further away. This differential force is known as tidal force. Near the black hole, tidal forces become so extreme that they can stretch objects into long, thin shapes, resembling strands of spaghetti. When anything, whether a space probe, an asteroid, or an unfortunate astronaut, ventures too close to a black hole, the side nearest to the black hole experiences a much stronger gravitational pull than the side facing away. For a human, the stretching force at your feet would be incredibly stronger than at your head, elongating your body into a long, thin shape. This process continues as you get closer, meaning you become more stretched out and also squeezed sideways. Eventually, the stretching becomes so severe that whatever falls in is torn apart at the atomic level, forming a stream of particles that spirals inexorably into the black hole. This dramatic and somewhat grisly fate serves as a stark reminder of the powerful and mysterious forces at work in our universe, forces that remain largely unobserved outside the context of theoretical physics and astronomical speculation. Even the largest structures, such as stars, are not immune to these forces. Spaghettification explains why they too can be torn into streams of glowing gas when they venture too close, contributing to the spectacular accretion disks that scientists observe as bright emissions around black holes. Black holes trap light by virtue of their extraordinarily strong gravitational fields, which are a consequence of their immense mass compressed into an incredibly small volume. This gravitational pull is so intense that beyond a certain boundary, known as the event horizon, not even light, the fastest entity in the universe, can escape. The event horizon represents the point of no return. Once anything crosses this threshold, it inevitably spirals inward towards the singularity, the infinitely dense core of the black hole. Einstein's theory of general relativity explains that gravity is a result of the curvature of spacetime caused by mass. A black hole bends spacetime so severely that it creates a sort of gravitational well. Even particles of light or photons, which typically travel in straight lines, are pulled into this well and cannot climb out. This complete inability to escape is why black holes appear black. They emit no light by themselves and reflect none. All that can signify their presence are indirect observations, such as X-rays emitted by the hot accelerated gas swirling in the accretion disk around them, or the gravitational waves produced by their interactions with other massive objects. Moreover, the invisibility of black holes makes them especially enigmatic and perilous. Their detection relies on observing the effects of their intense gravity on nearby stars and gas clouds, or the gravitational waves they produce when merging with other black holes or neutron stars. This invisible nature underscores their moniker as cosmic vacuum cleaners, consuming any matter that strays too close while themselves remaining shrouded in darkness. This duality of being both immensely powerful and incredibly elusive captures the imagination of scientists and cosmology enthusiasts alike, driving ongoing research and discovery in the field. When two black holes merge, the consequences are nothing short of cosmic fireworks, though not in the sense of visible light. Instead, these colossal events release an enormous amount of energy in the form of gravitational waves. First predicted by Albert Einstein's theory of general relativity, gravitational waves are ripples in the fabric of spacetime itself, generated by the acceleration of massive objects like merging black holes. These waves travel across the universe at the speed of light, carrying with them information about their cataclysmic origins. As the black holes spiral closer together in an intricate gravitational dance, they lose energy through the emission of these gravitational waves. This shrinking orbit accelerates the black holes, causing them to emit waves more energetically and rapidly until they finally collide. At the moment of merger, a single larger black hole forms, accompanied by a dramatic outburst of gravitational waves. These waves carry away a portion of the total mass energy of the system. For instance, when the Laser Interferometer Gravitational Wave Observatory, LIGO, first detected such a merger in 2015, it was estimated that energy equivalent to 3 solar masses was radiated away as gravitational waves in a fraction of a second. The resulting black hole from the merger is typically more massive than either of the original black holes, but slightly less than their combined mass due to the energy radiated away. These detections of gravitational waves provide scientists with a new way to observe the universe, offering insights into the properties and behaviors of black holes and validating Einstein's century-old predictions. They also open windows into understanding the formation and evolution of galaxies, as mergers of black holes are thought to play key roles in these grand cosmic architectures. Black holes can cause gravitational waves that ripple through the fabric of spacetime by their immense mass and the dynamic and violent processes they undergo, such as merging or rapidly accelerating motions. Einstein's theory of general relativity provides the framework for understanding this phenomenon. It posits that massive objects cause a distortion in spacetime, akin to a heavy ball placed on a trampoline causing a dip in the fabric. If these massive objects move in a non-uniform way, they generate ripples or waves in spacetime. These are the gravitational waves. When two black holes are caught in each other's gravitational grip, they begin to spiral towards one another, losing energy in the form of emitted gravitational waves. As their orbit decays, they spin faster and move closer together, causing increasingly strong gravitational waves that carry immense energy. Near the climax of their inspiral, the waves reach their peak intensity. When the black holes finally collide and merge, the event releases a sudden massive burst of gravitational waves, propagating outward at the speed of light. This enormous release of energy shakes the very fabric of spacetime, spreading these disturbances across the universe. Detectors like LIGO and Virgo have been designed specifically to catch these fleeting ripples. They use laser interferometry to measure the incredibly minute changes in distance caused by passing gravitational waves, changes that are fractions of the diameter of a proton. These detections not only confirm the dynamic nature of spacetime predicted by general relativity, but also provide a novel way of observing events in the universe that were previously hidden from view. By capturing these waves, scientists can gather information about the mass, spin, and distance of the merging black holes, opening new avenues for exploring the cosmos and understanding the fundamental nature of gravity itself. If Earth were to get caught in a black hole's event horizon, the consequences would be nothing short of catastrophic and terminal. The event horizon is the boundary around a black hole beyond which nothing, not even light, can escape its gravitational pull. As Earth approached this boundary, the immense gravitational forces of the black hole would begin to exert devastating tidal forces on our planet. Initially, the side of Earth facing the black hole would start experiencing a stronger gravitational pull than the side facing away, leading to what's known as tidal stretching. This differential force would become so extreme near the event horizon that Earth would be pulled apart in a process akin to, but far more intense than, the tidal forces we experience from our moon. As these forces grew, they would deform Earth into a long, thin shape before ultimately breaking it apart entirely. This process, dramatic and destructive, is often referred to as spaghettification. Once parts of Earth cross the event horizon, they would be doomed to an inexorable descent into the black hole's singularity, a point of infinite density where the known laws of physics break down. All matter from our planet would be crushed and compacted into this singularity, losing any recognizable structure or form. The immense energies released during this process would also likely contribute to the glowing accretion disk around the black hole, emitting high-energy radiation such as X-rays. For humans, any approach near the event horizon would be instantly terminal due to these overwhelming forces. The prospect of Earth encountering a black hole remains a theoretical scenario with extraordinarily low probability, but it underscores the awe-inspiring and fundamentally destructive nature of these cosmic entities. Black holes can emit deadly gamma-ray bursts, GRBs, during certain dramatic cosmic events, such as when they form or when they interact with other celestial bodies. Gamma-ray bursts are the universe's most powerful explosions, capable of emitting as much energy in a few seconds as the Sun will produce over its entire 10 billion-year lifetime. These intense bursts of gamma rays can arise from two primary scenarios involving black holes. The first scenario is the collapse of a massive star in a supernova event, leading to the formation of a black hole. As the star's core collapses under gravity, the outer layers are blown away in an explosive outburst. During this process, if the conditions are right, powerful jets of relativistic particles can be launched along the star's rotational axis. These jets punch through the collapsing star and break out into space, producing a gamma-ray burst that is extremely energetic and can last from a few seconds to several minutes. This type of GRB is known as a long-duration burst. The second scenario involves the merger of two neutron stars or a neutron star with a black hole. As these dense stellar remnants spiral towards each other, they emit gravitational waves, losing energy and causing their orbits to shrink further. When they finally collide, the immense energy released in the collision can give rise to a short-duration gamma-ray burst, typically lasting less than 2 seconds. The merger produces an accretion disk around the newly formed black hole, and magnetic fields can channel some of this material into narrow, highly focused jets that emit gamma rays. Both types of events, stellar collapses and binary mergers, produce black holes and environments that facilitate the formation of these jet structures. The jets themselves are formed because of the extreme magnetic fields and intense rotational energy involved in the processes. As these jets travel through space, they can be detected by orbiting telescopes like NASA's Fermi Gamma-ray Space Telescope, and they provide essential clues about the mechanics of black hole formation and the violent dynamics of our universe. If a gamma-ray burst were to aim directly at Earth, even from thousands of light-years away, the consequences could be dire. It could strip away the atmosphere's protective ozone layer, leading to increased radiation on the surface, affecting all forms of life. However, considering the vastness of space, the likelihood of a GRB with a direct hit on Earth is extremely low. Yet, studying these bursts remains crucial for understanding the life cycles of stars and the formation of black holes. Micro-black holes, often referred to as miniature or primordial black holes, are hypothetical tiny black holes that could be much smaller than stellar mass black holes. According to some theories, they might have formed in the early universe due to high-energy processes during the Big Bang, where intense pressure and temperatures could squeeze regions of space into dense, compact objects. These black holes could have masses comparable to that of a mountain, yet be confined within a space smaller than a proton. One of the fascinating aspects of micro-black holes is their size and their associated Hawking radiation, a theoretical prediction by physicist Stephen Hawking. According to Hawking's theory, black holes can emit particles due to quantum effects near their event horizons, effectively causing them to lose mass and eventually evaporate. The smaller the black hole, the more intense the Hawking radiation it emits, which means that micro-black holes could theoretically evaporate completely over time, releasing bursts of energy. As for their danger, the general consensus in the scientific community is that micro-black holes, if they exist, would pose minimal threat to Earth. Their small size would mean they evaporate quickly due to Hawking radiation, releasing energy but not enough to cause significant harm on a cosmic scale. Even if micro-black holes were produced in high-energy experiments, such as those conducted at the Large Hadron Collider, LHC, the expectation is that they would evaporate almost instantaneously, posing no real danger to their surroundings. The energies involved in these experimental setups are also far lower than the conditions of the early universe, making the creation of such black holes highly improbable. Nevertheless, the study of micro-black holes holds substantial value for theoretical physics. They could provide insights into the nature of gravity, quantum mechanics, and the fabric of space-time itself. Exploring these theoretical entities allows scientists to test the limits of our understanding and promotes advancements in our knowledge of the universe's most fundamental principles. When two galaxies collide, the event is an awe-inspiring ballet of cosmic proportions, one that unfolds over hundreds of millions to billions of years. Contrary to the word collision, which might evoke images of catastrophic impacts, the vast spaces between stars mean that actual stellar collisions are rare. Instead, what transpires is a complex gravitational interaction that dramatically alters the structure and fate of both galaxies involved. As the galaxies approach each other, their mutual gravitational attraction starts to pull them together, distorting their shapes. Tidal forces stretch and warp the galaxies, often creating elongated streams of stars and gas known as tidal tails. These interactions can trigger bursts of star formation as clouds of gas are compressed and ignite in a frenzy of new star births. Entire regions can light up with stellar nurseries, forming bright and young star clusters. At the heart of most galaxies lies a supermassive black hole, and when two galaxies merge, their central black holes can eventually coalesce into a single, even larger supermassive black hole. As these black holes spiral inwards and merge, they can emit strong bursts of gravitational waves, further enriching the cosmos's dynamic fabric. The relentless gravitational chaos during the merger can also fling stars into new orbits or even eject them from the galaxies entirely, contributing to the population of rogue stars drifting through intergalactic space. Over time, the galaxies will settle into a new, more stable configuration. Depending on their initial sizes and structures, the result can vary dramatically. For example, a collision between two spiral galaxies often results in the formation of an elliptical galaxy, characterized by a more homogeneous spheroidal shape. The Milky Way itself is on a collision course with the Andromeda Galaxy, a distant event slated to occur in about 4 billion years. When that time comes, the two galaxies will dance around each other, eventually merging into a single larger galaxy that astronomers have nicknamed Milkomeda. The consequences of such galactic mergers reshape the galaxy's fates and provide a natural laboratory for studying the processes of galaxy evolution, stellar formation, and the interplay of massive black holes. These cosmic events are among the most magnificent and transformative phenomena in the universe, leaving indelible marks on the structure and contents of the galaxies involved. A massive asteroid impact could potentially end life on Earth through a series of catastrophic events and ensuing environmental changes. The energy released upon such an impact would be devastating, comparable to the detonation of several billion nuclear bombs simultaneously. This energy would manifest as intense heat, shockwaves, and seismic activity strong enough to cause immediate widespread destruction. Upon striking Earth's surface, the asteroid would create a massive crater and throw immense quantities of dust and debris into the atmosphere. The immediate vicinity of the impact site would experience violent fires, hurricanes, force winds, and colossal tsunamis if the impact occurred in oceans. However, these hazards, while deadly, are only the beginning. The real global threat comes from the aftermath, particularly the drastic climatic shifts often referred to as an impact winter. The dust and aerosols ejected into the stratosphere would block sunlight, significantly reducing the amount of solar radiation reaching the Earth's surface. This would lead to a severe drop in global temperatures, plunging the planet into a prolonged period of cold and darkness. The lack of sunlight would severely impair photosynthesis, leading to the collapse of food chains starting from phytoplankton in the oceans to terrestrial plants. As primary producers die off, herbivores and subsequently carnivores, including humans, would struggle to find food, leading to mass starvation. Additionally, the environmental changes could trigger acid rain as sulfur compounds from vaporized rock combine with atmospheric moisture, further poisoning water sources and soil. The combination of cold temperatures, failing ecosystems, and toxic conditions could make survival incredibly difficult. Evidence of such impacts in Earth's history highlights their potential for mass extinction. The most famous example is the asteroid impact that occurred around 66 million years ago, widely believed to have caused the Cretaceous-Paleogene extinction event, eliminating about 75% of all species, including the non-avian dinosaurs. While current asteroid, comet detection programs and space agencies actively monitor near-Earth objects, giving us some level of preparedness, the sheer scale of an asteroid impact emphasizes our planet's vulnerability to such catastrophic natural events. Gamma-ray bursts, GRBs, are incredibly energetic events that produce intense bursts of gamma rays, the highest energy form of light. These bursts are the most luminous electromagnetic events known to occur in the universe, capable of emitting as much energy in a few seconds as the Sun will produce over its entire 10 billion-year lifespan. The origins of GRBs are typically associated with catastrophic cosmic events, such as the collapse of massive stars into black holes or the merger of neutron stars. GRBs are generally divided into two categories based on their duration: long-duration GRBs, which last more than 2 seconds and are usually associated with the collapse of massive stars, and short-duration GRBs, which last less than 2 seconds and are typically linked to the merger of neutron stars. Both types generate jets of highly accelerated particles that emit gamma rays as they collide with surrounding material at near light speeds. If a GRB were to occur close to Earth and its jet were aimed directly at our planet, the consequences could be devastating for life. One of the primary dangers is the intense burst of gamma radiation, which can cause severe damage to the Earth's atmospheric chemistry. Gamma rays have the capability to ionize molecules in the atmosphere, leading to the formation of nitrogen oxides. These compounds can break down the protective ozone layer, which shields the Earth's surface from harmful ultraviolet (UV) radiation. With the ozone layer compromised, increased levels of UV radiation would reach the surface, which could lead to widespread destruction of DNA molecules, causing lethal mutations across many forms of life, from phytoplankton in the oceans to terrestrial plants and animals. Another consequence of a nearby GRB could be the triggering of a gamma-ray burst winter. The initial burst would be followed by the formation of nitrates in the atmosphere, potentially causing intense, long-lasting cooling. This cooling could mimic the effects of nuclear winter, leading to a significant drop in global temperatures, disrupting ecosystems, and causing food shortages. Historical evidence suggests that past mass extinction events may have been influenced by similar cosmic events, although conclusive proof remains elusive. Fortunately, because GRBs are extremely rare and occur predominantly in distant galaxies, the likelihood of Earth being directly targeted by one is exceedingly low. However, understanding and monitoring such phenomena is crucial, as they remind us of the potential existential threats that our planet faces from the vast and dynamic cosmos. A supernova explosion can have profound and potentially devastating effects on nearby planets due to the enormous amounts of energy and material it ejects into space. When a massive star reaches the end of its life and explodes as a supernova, it releases more energy in a few seconds than our Sun will emit in its entire lifetime. This cataclysmic event sends shockwaves and a flood of radiation racing through the surrounding space, significantly affecting any nearby planetary systems. The immediate effect of a supernova on nearby planets would be the intense burst of radiation. This radiation includes X-rays, gamma rays, and ultraviolet light, which can strip away a planet's atmosphere if it is sufficiently close to the explosion. The loss of an atmosphere would expose the planetary surface to direct cosmic and solar radiation, making it inhospitable to life as we know it. Mars, for example, is believed to have lost much of its atmosphere through different processes, giving us a small-scale example of what could happen on a larger scale due to a nearby supernova. In addition to radiation, the supernova ejects massive amounts of high-energy particles known as cosmic rays into space. These particles can penetrate planetary atmospheres and surfaces, causing further ionization and increasing radiation levels. Prolonged exposure to such cosmic rays could lead to severe mutations or death for any biological organisms, effectively sterilizing the planet. The immense shockwave from the supernova can also have physical impacts on nearby planets. If a planet is within a few light-years of the explosion, the shockwave could compress planetary atmospheres, causing significant heating and potential climatic upheavals. Moreover, the influx of heavy elements ejected by the supernova could lead to changes in the chemical composition of planetary atmospheres and surfaces, creating new molecules or destroying existing ones that are crucial for life. Over longer periods, the material ejected from a supernova can contribute to the formation of new stars and planets, seeding them with heavy elements like carbon, oxygen, and iron, elements essential for the development of life. However, for any planets too close at the time of the explosion, the immediate destructive effects far outweigh any potential benefits. While no stars within the critical distance are expected to explode as supernova imminently, studying these events helps scientists understand the life cycles of stars and the environments of planets in our galaxy. Our relative safety from such colossal explosions is a reminder of the delicate balance within our cosmic neighborhood that allows life on Earth to flourish. Imagine the celestial ballet of nature's most exotic objects in the annals of cosmic history, a neutron star and a black hole on a fateful collision course. As they draw closer, the gravitational forces between them crescendo into a gravitational symphony, detectable by the most sensitive detectors on Earth, such as LIGO and Virgo. The neutron star, a remnant core of a massive star, with a mass 1.5 times that of our Sun, yet packed into a sphere just 20 kilometers across, edges closer to the black hole's event horizon. Here, space-time itself is so severely curved that nothing, not even light, can escape the black hole's ravenous maw. As the neutron star spirals inward, tidal forces distort its shape, elongating it, almost like a cosmic spaghetti noodle stretching toward the event horizon. Material from the neutron star starts to get stripped away and forms an accretion disk around the black hole, heating up to millions of degrees and emitting X-rays that can be detected across billions of light years. When the final leap happens, the neutron star succumbs entirely to the black hole's gravitational grasp, merging swiftly. This cataclysmic union releases a burst of gravitational waves, ripples in the fabric of space-time, that journey across the universe, providing paramount proof of the striking event and enriching our understanding of relativistic astrophysics. Consider the dazzling journey of a comet, traveling vast interstellar distances before its icy core meets its doom in a collision with Earth. This cosmic intruder enters our atmosphere at breathtaking speeds, often exceeding 20 times the speed of sound, a celestial bullet that can be kilometers wide. The sheer kinetic energy released upon impact is unfathomable, equivalent to millions of nuclear bombs detonating simultaneously. When it collides with the Earth's surface, the comet delivers a cataclysmic punch, excavating a crater possibly hundreds of kilometers in diameter and vaporizing itself and everything in its immediate vicinity. The aftermath of such an impact extends far beyond the crater. The collision throws massive quantities of dust and debris into the atmosphere, creating a shroud that can envelop the entire planet, blocking sunlight for months or even years. This lack of sunlight disrupts photosynthesis, leading to a collapse of food chains starting from tiny oceanic algae to colossal land-dwelling dinosaurs. Additionally, the impact can trigger wildfires, acidic rain, and long-term climatic changes, such as a plummeting global temperature, a phenomenon often referred to as an impact winter. Combined, these effects can be devastating enough to drive a significant portion of Earth's species to extinction, marking the end of entire eras within the geological timeline. The infamous Chicxulub impact, linked to the mass extinction event that wiped out the non-avian dinosaurs approximately 66 million years ago, stands as a testament to the catastrophic potential of comet impacts. Interstellar objects, such as the enigmatic Oumuamua, pose fascinating opportunities and potential risks as they traverse our solar system. Unlike typical comets and asteroids that originate within our solar neighborhood, Oumuamua arrived from the vast expanse of interstellar space, moving on a hyperbolic trajectory that ensured it would never return. Although its passage was brief, lasting merely weeks from detection in late 2017 to its exit, the implications of such encounters are profound. Scientifically, interstellar objects carry the secrets of other star systems. They are time capsules of distant regions of the Milky Way. However, their unpredictable paths and characteristics introduce an element of uncertainty. Their trajectories are not fully mapped, and their velocities are much higher compared to the typical objects near Earth, potentially reducing the reaction time for any needed Earth-protecting actions. While Oumuamua itself posed no threat, other interstellar wanderers could hypothetically harbor different risks, such as collision potential or unknown material compositions that could have unforeseen interactions with our atmosphere or planetary surfaces. The key danger lies in our limited capability to detect and predict these interstellar visitors early enough to devise appropriate strategies, underscoring the imperative for advanced astronomical monitoring systems and preparedness plans. These celestial interlopers serve as a cosmic reminder of the dynamic and occasionally perilous nature of our place in the universe. Visualize a rogue star, an untethered celestial wanderer drifting through the cosmos, and consider the dramatic consequences if it were to pass close to our solar system. Unlike the Sun and its steadfast companions in the Milky Way, rogue stars are gravitationally unbound, moving through the galaxy at random, often at tremendous speeds. If one of these stellar nomads were to venture perilously close to us, its gravitational influence could wreak havoc on the delicate balance of our solar system. As the rogue star approaches, its immense gravitational pull could perturb the orbits of planets, asteroids, and comets. Even a star passing within a light year a considerable distance by terrestrial standards, could exert enough force to destabilize the Oort cloud, a distant spherical shell of icy bodies surrounding our solar system. This could send a shower of comets inward, increasing the likelihood of impacts on planets, including Earth. Closer encounters, though exceedingly rare, could have even more profound effects. The orbits of planets might be altered dramatically. Some might be ejected from the solar system entirely, while others could collide due to shifted trajectories. The delicate dance that sustains life on Earth could be disrupted, potentially reducing our planet to an uninhabitable wasteland. This hypothetical scenario underscores the fragility of our cosmic neighborhood and the profound interconnectedness of gravitational forces at play. It serves as a reminder of the vast, largely unpredictable dynamism that governs the universe. Imagine the sudden and spectacular death of a massive star, a supernova explosion occurring in our cosmic neighborhood. This cataclysmic event releases an unfathomable amount of energy, with luminosity exceeding that of an entire galaxy momentarily. If such a supernova were to occur within a few dozen light-years of Earth, the potential effects could be monumental and far-reaching, altering life as we know it. First, the immediate impact would be a drastic increase in cosmic radiation. The initial burst of gamma rays, although lasting only seconds to minutes, would deliver an intense dose of radiation to our planet's atmosphere. This could deplete the ozone layer, our primary shield against the sun's ultraviolet radiation, leading to significant increases in surface UV levels and thereby elevating risks of skin cancer and other biological consequences. Over subsequent years, the influx of high-energy particles known as cosmic rays would further permeate our atmosphere. These particles could induce atmospheric chemistries that are not normal, producing nitrogen oxides that exacerbate ozone depletion and potentially alter climate patterns by triggering cooling mechanisms in the stratosphere. The longer-term repercussions encompass both terrestrial and marine ecosystems. The loss of the ozone layer and climate shifts can disrupt food chains, from phytoplankton in the oceans to terrestrial plants. Historical evidence even suggests that supernovae might be linked to mass extinction events. Scientists speculate that a supernova around 2.5 million years ago could have contributed to marine megafauna extinction at the Pleistocene epoch's onset. Thus, a nearby supernova is not merely an astronomical event to behold. It is a consequential cosmic phenomenon capable of altering the intricate biological and atmospheric webs that sustain life on Earth, a humbling reminder of the universe's dynamic and sometimes perilous nature. Imagine the colossal energy unleashed when two celestial titans like galaxies or black holes collide. These cosmic collisions don't merely involve the direct impacts of stars smashing into each other. The real force lies in the gravitational interactions and the resultant shockwaves that can ripple through entire solar systems. As these vast structures merge, they generate gravitational shockwaves that propagate at incredible speeds, disturbing everything in their path. When such a shockwave penetrates a solar system, its gravitational influence can be catastrophic. Planets may be yanked from their stable orbits, spiraling into their host stars or being flung into interstellar space as rogue planets. This chaos extends to smaller bodies like asteroids and comets, which could be sent on collision courses with planets, increasing the likelihood of catastrophic impacts. The very solar winds that shape the protective heliosphere around a system could be disturbed, exposing planets to higher levels of cosmic radiation. Such disruptions would jeopardize any delicate balances necessary for sustaining life, as the delicate choreography of orbits that has persevered for billions of years is thrown into disarray. Furthermore, the sheer energy involved in these collisions can compress interstellar gas and dust, igniting regions to form new stars while possibly extinguishing existing ones by stripping away their gas reservoirs. This duality of creation and destruction exemplifies the violent beauty of the universe. Hence, the shockwaves from cosmic collisions act as a palpable reminder of the immense forces at play, capable of turning entire solar systems into celestial pinball machines, underscoring the transient and often precarious nature of galactic structures. Envision a Magnetar, one of the universe's most formidable entities, a type of neutron star with a staggering magnetic field. 1,000 times stronger than that of a typical neutron star, and a quadrillion times that of Earth's magnetic field. These celestial powerhouses originate from the remnants of supernova explosions, compressing a star's core into an incredibly dense and highly magnetized object only a dozen kilometers across. The magnetic field of a magnetar is so intense it can distort atomic structures and generate violent bursts of X-rays and gamma rays. Should the Earth be relatively close to a magnetar during one of its magnetic flares, the resulting magnetic storm could have cataclysmic effects on our technology. The formidable magnetic field could induce enormous electrical currents in our planet's magnetosphere, akin to the solar storms caused by coronal mass ejections, but exponentially more powerful. These induced currents could overload and damage satellites, disrupt GPS coordinates, interfere with communication signals, and potentially knock out large swathes of the electrical grid. Transformers could be fried, and power outages could span continents. On a more immediate scale, the burst of high-energy radiation could affect electronic circuits on the surface, perpetrating a massive electromagnetic pulse, EMP. Sensitive electronics, from smartphones to medical devices and computers, could be rendered useless. Magnetar's proximity could plunge the modern world into a technological dark age, underscoring the fragility of our engineered systems in face of such formidable cosmic forces. Although magnetars are typically distant and the probability of such an encounter is low, the hypothetical scenario serves to highlight the titanic energies at play in the cosmos and the vulnerability of our technological civilization. Supernovae are among the most powerful explosions in the universe, the cataclysmic death throes of massive stars that have burned through their nuclear fuel. When a star at least 8 times the mass of the Sun reaches the end of its life cycle, it either collapses into a neutron star or black hole and subsequently blows off its outer layers in a supernova. This explosion can outshine an entire galaxy for weeks and release more energy in a few months than the Sun will emit in its entire lifetime of about 10 billion years. Imagine this as the simultaneous detonation of 1 trillion hydrogen bombs. The sheer scale of energy is beyond ordinary comprehension. If a supernova were to occur within about 50 light-years of Earth, the consequences could be catastrophic for life as we know it. The initial blast of gamma rays would have the potential to strip away the Earth's ozone layer, our primary defense against the Sun's harmful ultraviolet radiation. Without this protective shield, increased UV radiation could lead to widespread biological damage, notably an elevated incidence of skin cancers and the disruption of photosynthesis in plants, which could collapse ecosystems and agricultural systems alike. Moreover, the influx of cosmic rays would result in increased atmospheric ionization, producing nitrogen oxides that can further degrade the ozone layer and potentially trigger a nuclear winter effect by altering climate patterns. Additionally, historical data suggests supernovae may have influenced mass extinction events. Evidence points to a possible link between a supernova explosion and the Devonian extinction around 359 million years ago, when an unusual spike in UV radiation damaged terrestrial and marine organisms that rely on photosynthesis. Although no candidate for imminent nearby supernova looms in our stellar neighborhood, the staggering power of such an explosion underscores the delicate balance of conditions that sustain life on Earth and the ever-present potential for radical cosmic changes. A hypernova is the cosmic equivalent of a supernova on steroids, an event so powerful that it makes a typical supernova seem almost modest by comparison. Hypernovae are thought to occur when exceptionally massive stars, those with over 30 times the mass of our Sun, end their lives in cataclysmic detonations. The core of these giants collapses directly into a black hole, unleashing immense energy in a matter of moments. This culminates in a burst of gamma rays, known as a gamma ray burst, which can release as much energy in just a few seconds as our Sun will produce over its entire 10 billion-year lifespan. The sheer magnitude of a hypernova's energy release makes it far more terrifying than a regular supernova. If one of these titanic explosions were to occur within a few thousand light-years of Earth, the resulting gamma-ray burst and high-energy particles could dramatically impact our planet. The initial onslaught of gamma rays would have the potential to strip away Earth's ozone layer, much like in a supernova event, but on an even grander scale. This would expose the surface to lethal levels of ultraviolet radiation, with devastating consequences for all forms of life. Furthermore, The high-energy cosmic rays could lead to significant atmospheric ionization, producing chemical changes that may plunge the planet into a prolonged phase of climatic upheaval, sometimes referred to as an impact winter. Historical research suggests that gamma-ray bursts from hypernova might have driven mass extinction events in Earth's past, although direct links remain theoretical. Still, the notion of a hypernova happening in our cosmic vicinity poses a daunting threat. Unlike the gradual changes emitted by more familiar astronomical events, the effects of a hypernova would be quick, far-reaching, and catastrophic. The fact that these events are exceedingly rare and occur far from our solar system is a relief, but the potential destruction they represent serves as a humbling reminder of the universe's vast and often unpredictable dynamism. Pulsars are the extraordinarily dense remnants of massive stars that have exploded in supernovae, leaving behind a neutron star with highly concentrated mass and a magnetic field. Spinning at incredible speeds, some rotating multiple times per second, pulsars emit beams of electromagnetic radiation from their magnetic poles. These beams sweep through space like the beams of a lighthouse due to the misalignment between the pulsar's magnetic axis and its rotational axis. The radiation emitted from these beams is not just ordinary light. It encompasses a broad spectrum, ranging from radio waves to highly energetic X-rays and gamma rays. Imagine if a pulsar were close enough for its radiation to intersect with Earth. When these devastating beams of energy collide with a planet, they have the potential to cause severe biological and atmospheric damage. The unrelenting flux of high-energy particles can ionize the atmosphere, producing nitrogen oxides that deplete the protective ozone layer. Without this critical shield, harmful ultraviolet radiation from the sun could bombard the planet's surface, rendering it inhospitable by increasing the risk of radiation-induced illnesses and disrupting the delicate balance of ecosystems. Moreover, the intense radiation could interfere with electronic systems and communications, disrupting modern technology while simultaneously posing grave risks to living organisms through increased cancer rates and other radiation-related health issues. Historical models suggest that pulsar emissions could be responsible for sterilizing planets within close proximity, effectively wiping out potential life forms regardless of their biological complexity. While the chances of Earth falling within the deadly beam of a nearby pulsar are extremely slim, such a scenario illustrates the immense power and peril inherent in some of the universe's most fascinating objects. This captivating but daunting possibility underscores the precariousness of our existence on this tiny blue dot, adrift in a cosmos filled with both wonder and danger. Quasars stand as among the most luminous and energetic phenomena in the universe, manifesting the ferocity of supermassive black holes at the hearts of distant galaxies. These cosmic powerhouses are essentially the heavily accreting centers of galaxies where a supermassive black hole, millions to billions of times the mass of our Sun, voraciously devours surrounding matter. This matter, as it spirals inward, forms a superheated accretion disk that blazes brightly across the electromagnetic spectrum, often outshining the combined stellar light of the host galaxy. The energy output of a quasar is incomprehensible, frequently exceeding that of 1 trillion suns. This intense radiation, spanning radio waves, visible light, ultraviolet rays, X-rays, and gamma rays, can incinerate anything unfortunate enough to be too close. The energetic particles and radiation emitted can strip electrons from atoms, effectively ionizing and destroying molecular structures. Within a couple of light years, the searing radiation would sterilize planets by obliterating atmospheres and rendering surfaces uninhabitable. The high-energy jets emitted by quasars, which can extend for millions of light years, also contribute to this cosmic devastation. These jets, composed of charged particles traveling near the speed of light, bombard surrounding regions with intense radiation and high-energy particles, likened to a colossal cosmic blowtorch. For objects further away, the radiation pressure from a quasar can still exert formidable influence, heating interstellar gas and preventing the formation of new stars. This suppression of star formation can, in turn, quench galactic development for millions of years. The formidable energy output of quasars profoundly shapes the evolutionary trajectory of their host galaxies and any surrounding cosmic structures. While Earth is safely ensconced in a less active domain of space, The terrifying potential of quasars serves as a humbling reminder of the sheer scale of power present in our universe, a reminder of both its creative and destructive capabilities. Imagine a supernova, one of the universe's most spectacular yet catastrophic events, detonating within proximity of our solar system. While supernovae typically occur hundreds to thousands of light-years away, a nearby eruption within about 50 light-years could have profound and devastating effects on Earth. The radiation emanating from a supernova bombards space with energetic particles, including gamma rays and cosmic rays, which can interact with our planet's atmosphere in complex and perilous ways. Immediately following the explosion, the burst of gamma radiation would have the potential to severely damage or deplete the ozone layer, our primary defense against the sun's harmful ultraviolet UV radiation. This depletion could last for months or even years, exposing the Earth's surface to heightened levels of UV radiation, which can cause significant harm to all life forms. Increased UV levels can damage genetic material in living organisms, leading to higher mutation rates, cancer risks, and disruptions in ecosystems. For example, phytoplankton, the foundation of the marine food web, is particularly susceptible to UV damage, which can cascade through the entire oceanic ecosystem and impact global food resources. The prolonged influx of cosmic rays from a nearby supernova can also induce atmospheric chemistry changes. These high-energy particles can ionize nitrogen and oxygen molecules, leading to the formation of compounds like nitrogen oxides. Nitrogen oxides can catalyze the destruction of ozone molecules, further aggravating the depletion of the ozone layer. Additionally, these chemical changes can contribute to climatic shifts, such as cooling of the Earth's surface, leading to what scientists term an impact winter. This drop in temperatures can disrupt weather patterns, agricultural production, and even lead to mass extinctions if the environmental stress exceeds the resilience of existing species. Therefore, radiation from a supernova, by compromising the ozone layer and altering atmospheric chemistry, can induce a chain of biological and environmental upheavals. This highlights the interconnected vulnerability of Earth's systems to cosmic phenomena, underlining the significance of studying and understanding such stellar events within our galaxy. Blazars are one of the most extreme and energetic classes of active galactic nuclei found in the universe. At the heart of a blazar lies a supermassive black hole, millions or billions of times more massive than our Sun, voraciously consuming material from its surrounding accretion disk. What makes blazars particularly extraordinary is the orientation of their relativistic jets, beams of charged particles traveling at nearly the speed of light, aimed almost directly at Earth. These jets are powered by the immense gravitational and magnetic forces surrounding the black hole, converting matter into energy with astonishing efficiency. The energy output of these jets is truly staggering, capable of spanning vast cosmic distances and interacting with anything in their path. If a blazar's jet were to intersect with a solar system like ours, the consequences could be dire. The high-energy radiation, including X-rays and gamma rays, emitted by these jets can strip electrons from atoms, creating highly ionizing conditions. In the atmosphere, this ionization can lead to an increase in doses of harmful radiation reaching the surface, with devastating biological effects. For instance, a sudden influx of radiation could cause severe damage to DNA and cellular structures, elevating cancer risks and potentially leading to widespread biological disruptions. Even more alarmingly, the impact of such a radiation beam could compromise the integrity of Earth's atmosphere over time. The energetic particles could ionize atmospheric molecules, inducing complex chemical reactions that may diminish the protective ozone layer, increasing the planet's vulnerability to ultraviolet radiation from the sun. Moreover, the interaction of these extreme energies with our magnetic field could disrupt satellite operations, communication systems, and other technological infrastructure, plunging societies into chaos. The fact that blazars can affect objects over distances of millions of light-years underscores the immense power and potential danger of these astrophysical phenomena. While Earth is not currently in the direct path of any known blazar, understanding these cosmic hazards enhances our appreciation of the universe's dynamic and sometimes perilous nature, and underscores the critical importance of astronomical research in predicting and potentially mitigating such high-energy threats. Cosmic rays present a significant hazard to astronauts and space missions, posing challenges that extend beyond the vacuum of space. These high-energy particles originate from various stellar sources, including supernovae, the Sun, and distant galaxies, hurtling through space at nearly the speed of light. Unlike the relatively shielded environment provided by Earth's atmosphere and magnetic field, space offers little protection against these energetic particles. This lack of shielding means cosmic rays can penetrate spacecraft and spacesuits, delivering a relentless bombardment of radiation to anyone outside Earth's protective envelope. For astronauts, prolonged exposure to cosmic rays can have serious health implications. These high-energy particles can ionize atoms and molecules within human tissues, causing damage at the cellular and DNA levels. Such radiation exposure increases the risk of cancer, cataracts, and other degenerative diseases. The potential for acute effects like radiation sickness is also present, characterized by symptoms such as nausea, fatigue, and diminished cognitive function. In particular, heavy ions, one of the types of cosmic rays known as high atomic number and energy, HZE particles, pose significant risks due to their greater mass and energy, which can cause more extensive cellular damage compared to other forms of ionizing radiation. Space missions are also at risk mechanically and electronically. Cosmic rays can induce single-event effects, SEEs, in spacecraft electronics, causing bit flips or data corruption in critical systems. These events can lead to malfunctions in navigation, communication, and life support systems, potentially jeopardizing the entire mission. Prolonged exposure can degrade solar panels and other materials, shortening the lifespan of spacecraft. To mitigate these dangers, researchers and engineers are developing advanced shielding materials and radiation-hardened electronics, as well as exploring artificial magnetic fields to mimic Earth's protective properties. As humankind aspires to longer missions, such as journeys to Mars or permanent lunar bases, understanding and mitigating the dangers posed by cosmic rays will be crucial to ensuring the safety and success of space exploration. By addressing these challenges, we can better safeguard astronauts and fortify the spacecraft that journey through the cosmos, turning the dream of exploring Mars and beyond into reality while maintaining the health and safety of those courageous enough to venture into the final frontier. The universe is a grand stage for a multitude of extreme and violent phenomena, each showcasing staggering power and a magnitude that often defies human comprehension. Among the most dramatic of these events are gamma-ray bursts, GRBs, supermassive black hole mergers, and hypernovae, each representing a pinnacle of cosmic violence and energy. Gamma-ray bursts are perhaps the most intense explosions known, emitting enormous bursts of gamma-ray photons that can outshine entire galaxies for brief periods. These bursts are typically either the result of a massive star collapsing directly into a black hole, long-duration GRBs, or the merger of neutron stars or neutron-star black hole pairs, short-duration GRBs. The energy released in just a few seconds during a GRB can be equal to what the Sun will radiate over its entire 10 billion-year lifespan. These jets, if directed toward Earth, could potentially strip away the ozone layer, expose the surface to deadly ultraviolet radiation, and trigger extensive biological crises. Another example of cosmic cataclysm is the merging of supermassive black holes, typically found at the centers of colliding galaxies. When these titans of the universe converge, they create gravitational waves, ripples in the fabric of space-time that propagate across the cosmos. These mergers are so energetically potent that they unleash as much energy as multiple supernovae combined, momentarily warping space-time itself. The recent detections of these waves by observatories like LIGO and Virgo have confirmed the astonishing power of such mergers. Hypernovae, on the other hand, represent a more extreme form of supernova. Occurring when stars with more than 30 times the mass of our Sun collapse, hypernovae can produce energy levels that vastly exceed typical supernovae. These explosive deaths are believed to be associated with some of the most potent gamma-ray bursts, further enhancing their catastrophic potential. These events, each in their own right, highlight the incredible dynamics and violent nature of our universe. They serve as vivid reminders of the forces at play in the cosmos and the profound impact such phenomena can have, even over vast distances. As we continue to study these events, we deepen our understanding of the universe's extreme behaviors showcasing both its breathtaking beauty and its unfathomable power. The cosmos is a tapestry woven with breathtaking yet terrifying phenomena, and the most extreme events can send ripples across the universe with profound effects. Take supernovae, for example. These colossal explosions mark the violent death of a star and unleash a fury of energy. When a massive star reaches the end of its life cycle, its core collapses, unleashing an explosion that can outshine entire galaxies for a short period. The burst of radiation and ejected material from a supernova can trigger the formation of new stars and planetary systems. However, if a supernova were to occur within 30 light-years of Earth, it could pose serious threats. The intense gamma radiation and cosmic rays could damage our planet's ozone layer, which shields all life from harmful ultraviolet rays. This could lead to a significant increase in UV radiation reaching Earth's surface, potentially causing mutations or even mass extinctions. Additionally, let's not forget the dramatic dance of black holes, where extreme gravitational forces stretch and compress matter in a destructive tango. When two black holes spiral towards each other and eventually merge, they release gravitational waves, ripples in the fabric of space-time itself, that can be detected across vast cosmic distances. These waves have no direct effect on Earth's biosphere, but the knowledge we gain from observing them can reshape our understanding of the universe. Moreover, if a black hole passed close enough to our solar system, its immense gravitational pull could disrupt planetary orbits, leading to catastrophic consequences. Fortunately, such events are incredibly rare within the Milky Way. Nonetheless, the study of these cosmic titans enriches our grasp of fundamental physics and cosmology, illustrating just how interconnected and fragile our existence is within the grand cosmic ballet. Rogue planets, also known as interstellar or nomad planets, are fascinating wanderers of the cosmos, existing without a parent star to anchor them. These orphaned worlds are thought to be ejected from their original solar systems due to gravitational interactions and now drift through the galaxy in solitary voyages. Estimates suggest that for every star in the Milky Way, there could be at least 2 rogue planets, making them far more common than we might have previously imagined. Despite the cold and dark expanse they travel through, these planets could still harbor heat from radioactive decay or internal geological activity, potentially creating niche environments where life could theoretically survive. Should a rogue planet venture close to our solar system, its gravitational influence could disrupt the delicate balance that holds our celestial neighborhood together. Depending on its mass and trajectory, a rogue planet could perturb the orbits of comets in the Oort cloud or the Kuiper belt, sending a barrage of these icy bodies hurtling toward the inner solar system. The potential impact events could be catastrophic, reminiscent of the collision that is believed to have contributed to the extinction of the dinosaurs around 65 million years ago. On an even larger scale, if a rogue planet ventured close enough to the major planets, it could cause shifts in their orbits. Such changes might lead to climatic upheavals on Earth, disrupting the stable conditions that have allowed life to flourish. While the likelihood of such an event is low, the possibility underscores the dynamic and sometimes perilous nature of our cosmic environment. The prospect of a rogue asteroid hurtling towards Earth without warning is a scenario that stirs both scientific investigation and public imagination. Asteroids, specifically near-Earth objects, NEOs, are tracked meticulously by astronomers around the globe. Yet, with millions of these space rocks drifting in our cosmic vicinity, some of them may, theoretically, have the potential to bypass our current detection systems. As of now, NASA and other space agencies maintain vigilant observation networks using both ground-based telescopes and space-based observatories to catalogue NEOs. Asteroids larger than approximately 1 kilometer in diameter, which could cause global devastation, are thought to have been mostly identified and tracked. However, it's the smaller yet still hazardous asteroids, those ranging from a few meters to several hundred meters, that could surprise us. The likelihood of a small rogue asteroid sneaking past our defenses and striking Earth is relatively low but not negligible. Advances in astronomy have dramatically improved our ability to detect such intruders, yet the vastness of space and the limitations of our technology introduce an element of unpredictability. For instance, objects approaching from the direction of the Sun can be particularly challenging to spot due to the glare overwhelming our sensors. Recent technological initiatives, such as the upcoming Near-Earth Object Surveillance Mission, NEOSEM, and the European Space Agency's Fly-Eye telescope, are designed to enhance our early warning capabilities. Despite these efforts, the hypothetical sudden appearance of a rogue asteroid remains a valid reminder of Earth's vulnerability within the dynamic and vast universe. That said, international space agencies are also developing potential mitigation technologies, such as deflection strategies using spacecraft, to prepare for the unlikely but serious scenario of an asteroid impact. The traversal of a rogue star through our solar system is an astronomical scenario that borders on the cataclysmic, albeit with a remarkably low probability of occurrence. Rogue stars, often referred to as interstellar wanderers, would bring with them gravitational forces capable of wreaking havoc on the delicate orbital harmony of our planetary system. If such a stellar vagabond were to venture close to our solar system, its gravitational influence might distort the orbits of not only the planets, but also the myriad objects in the Kuiper Belt and Oort cloud, regions teeming with comets and asteroids. This gravitational disruption could potentially eject asteroids and comets from their usual orbits, sending them careening toward the inner solar system. The resulting increase in collision events poses a significant threat to Earth, reminiscent of the impacts believed to have caused mass extinctions in our planet's history. Additionally, the rogue star's passage could perturb the orbits of the planets themselves, potentially dragging them into new, destabilized paths or even ejecting them from the solar system entirely. Over millions of years, these altered orbits could drastically change Earth's climate, jeopardizing the stability and sustainability of life as we know it. While the direct intrusion of a rogue star is an exceedingly rare event, with estimates suggesting such occurrences might happen once every few billion years, the potential consequences underscore the interconnectedness and fragility of our cosmic neighborhood. It's a stark reminder of the forces at play in the universe and the relative serenity we currently enjoy within the solar system. Rogue black holes, invisible sentinels of immense gravitational might, traverse the cosmos with the potential for unseen but devastating consequences. These stellar remnants are typically the result of massive stars that have ended their life cycles, collapsing into points where gravity is so intense that not even light can escape. Unlike stars or planets, rogue black holes do not emit light, making them nearly impossible to detect through conventional means. Their presence is revealed only through their effects on nearby objects, such as the gravitational lensing of light from distant stars, or the erratic motion of stars and gas clouds in their vicinity. The most insidious danger a rogue black hole poses to planets, including those in our solar system, stems from its formidable gravitational pull. Should a rogue black hole wander into the vicinity of our solar system, its gravitational forces could vastly disrupt the orbits of planets, potentially flinging them into distant space or dragging them into spiraling deaths. Even without a direct encounter, the gravitational perturbations could destabilize the orbits of asteroids and comets in the Oort cloud, sending a hail of these objects into the inner solar system. The impact of such cometary bombardment could lead to catastrophic collisions with Earth, threatening life with massive environmental upheavals and mass extinctions. Moreover, the sheer mass of a rogue black hole could spawn tidal forces capable of stretching and squeezing planets, potentially leading to internal geological disturbances, increased volcanic activity, or even tectonic disruptions. While the probability of such a rogue black hole passing close enough to affect our solar system remains exceptionally low, the potential for such invisible threats is a reminder of the dynamic and often perilous nature of our universe. The continued advancement in astronomical technologies, including the study of gravitational waves and enhanced telescopic surveys, aims to increase our ability to detect these elusive cosmic wanderers and understand the risks they pose. Imagine a rogue planet, an untethered celestial body wandering the galaxy, finding its way into our solar system. The gravitational shockwaves from such an interloper could be profound, potentially setting off a chain reaction of orbital disturbances among the planets. Rogue planets, some of which may be as massive as Jupiter or Saturn, possess significant gravitational influence. As this rogue entity draws near, its gravitational pull could begin to tug at the orbits of outer planets like Neptune and Uranus, altering their paths and cascading down the gravitational chain to affect all planetary bodies, including Earth. The immediate consequence of these orbital modifications could be unpredictable climatic and environmental shifts on Earth. A shift in Earth's orbit, even by a small margin, could result in significant changes in our climate, oscillating between extreme heating or cooling. The agricultural systems that humanity relies on could face upheaval, potentially leading to global food shortages. The altered gravitational dynamics might also increase the prevalence of asteroid and comet impacts, as objects in the Kuiper belt and Oort cloud are perturbed and sent inward. The risk of a catastrophic collision with Earth would increase, reminiscent of the events believed to have precipitated the mass extinction of the dinosaurs, resulting in wide-scale environmental destruction and loss of life. Moreover, if the rogue planet's trajectory brought it too close to any of the gas giants like Jupiter or Saturn, the gravitational skirmish could lead to planetary ejections or significant orbital shifts. This would have far-reaching consequences beyond the immediate planetary environments, potentially destabilizing the entire solar system's architecture. While the chance of a rogue planet entering our solar system is exceedingly low, the dramatic potential outcomes underscore the delicate gravitational choreography that governs planetary orbits and the profound interconnectedness of celestial objects in our cosmic arena. The Oort cloud, a distant spherical shell of icy bodies surrounding our solar system, is a vast reservoir of comets, some of which can be dislodged and turned into potential Earth impactors. Rogue comets originating from this remote region can enter the inner solar system due to gravitational perturbations caused by passing stars, the galactic tide, or even the influence of hypothetical objects such as Planet 9. When these distant wanderers are nudged from their stable orbits, they begin their long journeys toward the Sun and, consequently, toward planets like Earth. As rogue comets travel inward, they can accelerate under the Sun's gravity, potentially crossing Earth's orbital path. Unlike asteroids, which typically reside within the asteroid belt between Mars and Jupiter, comets from the Oort cloud can be larger and travel at much higher velocities. Their icy composition sublimates as they approach the Sun, forming glowing comas and spectacular tails, but also increasing their fragmentation potential. This means that a single comet can break into multiple smaller yet still deadly fragments, each one posing a significant threat of impact. An encounter with such a rogue comet could lead to devastating consequences, resembling or surpassing historical impacts, such as the Chicxulub event that is believed to have led to the extinction of the dinosaurs about 65 million years ago. The challenge lies in detecting these rogue comets early enough to predict their trajectories and implement potential deflection or mitigation strategies. As these objects can come from any direction and have highly eccentric orbits, their unpredictable paths make them more difficult to track compared to near-Earth objects. However, advancements in wide-field survey telescopes and space-based observatories enhance our capacity to identify these icy wanderers earlier in their approach. Measures such as space missions designed to study comets up close, like the European Space Agency's Rosetta mission, provide valuable insights into their composition and behavior, which is critical for developing future impact prevention technologies. While the prospect of a rogue comet impact is fraught with peril, scientific vigilance and technological innovation continue to fortify Earth's defenses against such cosmic threats. The passage of a rogue neutron star near Earth would be an astronomical event of cataclysmic proportions, primarily due to the extraordinary gravitational forces these celestial objects exert. Neutron stars, the remnants of supernova explosions, contain a mass comparable to the Sun compressed into a sphere only about 20 kilometers in diameter. Despite their diminutive size, their gravitational pull is intense, capable of bending space-time and significantly influencing surrounding objects. If a rogue neutron star were to pass near our solar system, its gravitational forces could dramatically disrupt the orbits of planets, moons, and smaller celestial bodies. The immediate gravitational tug could cause planets to shift into new orbits, some potentially being ejected from the solar system entirely. On Earth, such a gravitational disturbance might lead to extreme tidal forces, exacerbating geological activity, triggering widespread earthquakes, volcanic eruptions, and tsunamis. The disruption of Earth's orbit could also lead to catastrophic changes in climate, rendering the planet inhospitable for current life forms. Moreover, neutron stars often emit intense radiation from their magnetic poles in the form of X-rays and gamma rays. If Earth were to be exposed to these beams, it could strip away the atmosphere and irradiate the surface, endangering all forms of life. Unlike black holes, which are entirely dark and would primarily exert gravitational threats, a neutron star's emissions add an additional layer of danger. The combination of gravitational disruption and radiation exposure could unleash a perfect storm of global devastation. The likelihood of such an event remains exceedingly low given the vast distances and the relative sparsity of neutron stars in our galactic neighborhood. However, understanding the potential consequences underscores the sheer power and unpredictability of the universe. Enhanced astronomical observations and continued study of these stellar remnants are crucial for better predicting and potentially mitigating the impacts of such rogue celestial phenomena on our solar system. Rogue objects, whether they are planets, stars, or even black holes, often travel through space undetected due to a combination of factors involving their intrinsic properties and the vast, dark expanse of the cosmos. One primary reason is the lack of intrinsic luminosity in many of these objects. Unlike stars, which emit significant amounts of light and can be observed across great distances, rogue planets and black holes do not shine on their own. Rogue planets, for example, might only reflect minimal starlight, and as they are usually far from any illumination sources, they remain incredibly difficult to spot. Similarly, a black hole does not emit light. It can primarily be detected by the gravitational effects it has on nearby matter or by the X-rays generated as it accretes material. Moreover, the sheer scale of the universe presents another formidable challenge. The vastness of space, filled with countless stars, galaxies, and other luminous objects, creates a crowded backdrop against which detecting relatively small, dark, and isolated rogue objects becomes akin to finding a needle in a cosmic haystack. Ground-based and space-borne telescopes equipped with advanced detection capabilities are designed to survey specific sections of the sky, but they can still miss rogue objects unless they are purposefully looking for gravitational anomalies or indirect signs of their presence. Technological and observational limitations also add to the challenge. As advanced as current telescopes are, they have limits in resolution and sensitivity, especially when it comes to detecting faint objects that do not emit light. Efforts to track and study these rogue objects often rely on secondary effects, such as gravitational lensing, where a massive object's gravity bends the light of more distant stars, or on the erratic motion of stars and other celestial bodies influenced by a nearby rogue. Initiatives like the upcoming Vera C. Rubin Observatory, which will survey the entire sky multiple times, aim to increase our chances of identifying these elusive roamers. Enhanced detection methods, including infrared and radio observations, can also help uncover the faint traces of rogue objects as they silently traverse the interstellar void. The implications of a rogue black hole consuming planets in its path are both fascinating and profoundly destructive, altering our understanding of cosmic events and the inherent dangers lurking in the universe. A black hole's immense gravitational pull is its defining feature, capable of capturing any object that comes too close, including entire planets. As a rogue black hole navigates through space without a host galaxy or stellar system anchoring it, it acts as a cosmic vacuum cleaner, potentially swallowing up planets, asteroids, and any matter in its trajectory. When a black hole encounters a planet, the gravitational forces exerted are so extreme that the planet would be stretched and compressed in a process known as spaghettification. The immense tidal forces stretch the planet along the axis pointing toward the black hole, while compressing it along the perpendicular axis, ultimately tearing it apart. As the planet's material spirals inward, it forms an accretion disk, heating up and emitting intense radiation before crossing the event horizon, from which nothing can escape. This dramatic interaction can have far-reaching implications. Firstly, the sudden disappearance of planets could destabilize the orbits of neighboring celestial bodies, potentially causing a cascade of gravitational disruptions within a given stellar system. Such disturbances could lead to additional planetary collisions or ejections, further contributing to cosmic chaos. Secondly, the intense radiation emitted by the accretion disk of a black hole consuming a planet could be detectable across vast distances, serving as a cosmic beacon that highlights these otherwise dark objects. Such emissions provide astronomers with rare opportunities to study black holes and the extreme physics governing their behavior. On a more speculative note, if a rogue black hole were to enter our solar system and consume planets such as Jupiter or even smaller members of our planetary family, the effects would be catastrophic. The gravitational chaos alone would likely render the solar system unrecognizable, disrupting the orbits of the remaining planets, potentially leading to collisions or sending them spiraling into the interstellar void. For Earth, this could mean drastic, life-ending environmental shifts or even outright annihilation. Though the probability of such an event is exceedingly low, the study of rogue black holes highlights the ever-present, albeit rare, dangers that exist within our universe, urging continuous vigilance and advancement in our cosmic awareness. Rogue objects such as wandering planets, stars, or black holes introduce a powerful element of chaos when they enter established star systems. The gravitational forces these nomadic objects exert can have profound and often catastrophic effects on the pre-existing harmony of celestial bodies within a star system. One of the most immediate impacts is orbital destabilization. When a rogue object approaches, its gravitational pull can alter the orbits of planets, moons, asteroids, and comets. Even minor perturbations can cascade through the system, leading to drastic shifts in orbital dynamics. For instance, a rogue planet drifting into a star system could perturb the orbits of existing planets. This gravitational nudge might cause planets to collide with one another, be ejected from the system entirely, or plunge into their host star. Planetary orbits that are stretched or compressed can lead to severe climatic changes on those planets, affecting their ability to support life. Additionally, altering the orbits of smaller bodies, such as asteroids or comets, could send a barrage of these objects into the inner regions of the system, increasing the likelihood of impact events that can drastically alter planetary landscapes and life conditions. An example of this would be the theorized Jupiter-Saturn interaction in our solar system's distant past, which may have dislodged comets from the Kuiper belt and affected impacts on Earth. The introduction of a rogue star or black hole amplifies these effects due to their immense gravitational influence. A passing rogue star could extend its gravitational reach across a wider area, causing a systemic upheaval. In the most dramatic scenarios, a rogue black hole's gravitational pull could cause extreme tidal forces, tearing apart planets and stars that venture too close, a phenomenon known as tidal disruption. The material from these celestial bodies would be drawn into an accretion disk around the black hole, heating up and emitting intense radiation. Such an event would not only disturb the local star system, but could also be detected across the galaxy, providing a stark reminder of the destructive potential of rogue objects. Rogue objects pose a significant threat to the stability of established star systems. Their gravitational influence can lead to orbital chaos, planetary ejections, catastrophic collisions, and intense radiation emissions, fundamentally transforming the dynamics of affected systems and potentially rendering previously habitable planets inhospitable. The rarity of such encounters highlights their dramatic nature and underscores the importance of ongoing astronomical surveillance and research to better understand these formidable cosmic wanderers. The universe is a vast and enigmatic expanse, filled with perplexing mysteries that continue to baffle scientists despite significant advancements in our understanding of cosmology. One of the most terrifying unknowns is the nature of dark matter and dark energy, which together make up approximately 95% of the universe's total mass energy content. Dark matter is thought to be a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter, such as galaxies and clusters of galaxies. Then there's dark energy, an even more mysterious force that's driving the accelerated expansion of the universe. Despite numerous theories and experiments, the true nature, origin, and properties of these dark components remain elusive, leaving us with the unnerving realization that most of the universe is composed of something entirely unknown to us. Another haunting enigma is the nature of black holes, especially the supermassive black holes that reside at the centers of galaxies, including our own Milky Way. While general relativity provides a framework for understanding many aspects of black holes, such as event horizons and singularities, the full picture, especially what happens inside a black hole, remains shrouded in mystery. Singularities, points of infinite density where the known laws of physics break down, pose a significant challenge to our understanding of space-time and force us to confront the limitations of current scientific theories. The information paradox, which questions what happens to information that falls into a black hole, adds another layer of complexity and suggests gaps in our understanding of quantum mechanics and general relativity. Then there are the questions of origin and ultimate fate. The Big Bang theory provides a robust framework for the beginning of the universe, yet it leaves open questions regarding what came before, if such a concept even makes sense in the context of time and space. Similarly, while we have scenarios for the end of the universe, whether it's the Big Crunch, Big Freeze, or Big Rip, each theory presents scenarios that are almost unfathomable to human experience. The true nature of time, the possibility of multiple universes or dimensions, and the potential existence of extraterrestrial life are additional unknowns that loom large in our explorations. These cosmic mysteries underscore the vastness of what we do not yet understand, presenting an eerie, awe-inspiring frontier for scientific inquiry. As we continue to probe the cosmos, we are reminded of both our progress and our profound limitations, navigating a universe that holds more questions than answers. The universe is a dynamic and often unpredictable place, and a sudden and unknown cosmic event could indeed have devastating effects on life on Earth. One such potential scenario involves a gamma-ray burst, GRB. These bursts are among the most energetic events in the universe, believed to result from the collapse of massive stars or the merging of neutron stars. A gamma-ray burst happening within our galaxy, but several thousand light-years away, could still impact Earth. The intense gamma radiation from such an event could strip away the Earth's ozone layer, which protects life from harmful ultraviolet rays from the sun. The sudden increase in UV radiation could lead to a spike in skin cancers, damage to plant life, and significant disruptions to the food chain, potentially triggering mass extinctions. Another catastrophic scenario might involve a supernova explosion of a nearby star. While most of the stars in our immediate vicinity are not candidates for such an explosion anytime soon, a supernova within 25 light-years could still pose a colossal threat. Besides emitting gamma and X-rays, supernova produce high-energy cosmic rays that could attack our atmosphere, once again depleting the protective ozone layer. This would not only allow dangerous UV radiation to penetrate, but potentially lead to a cosmic winter, where the sunlight is partially blocked by the aftermath of such an explosion. This cooling effect could devastate global agriculture, leading to food shortages and widespread ecological collapse. Lastly, we cannot dismiss the impact threat from a rogue asteroid or comet, even though wide-ranging detection programs have identified most of the larger near-Earth objects. A smaller, previously undetected object could still inflict considerable damage upon collision. Depending on its size and impact location, an asteroid strike could trigger tsunamis, wildfires, and an impact winter, where particulate matter thrown up into the stratosphere blocks sunlight, leading to global cooling and catastrophic disruptions to ecosystems. In all these scenarios, the element of unpredictability combines with our current technological limitations in detection and prevention, emphasizing Earth's vulnerability in the vast expanse of the cosmos. The continuous study and expansion of our observational capabilities remain crucial to improve our chances of predicting such events and developing mitigation strategies to protect life on Earth. The concept of humanity accidentally triggering a catastrophic cosmic event might seem like the realm of science fiction, but certain theoretical scenarios do raise concerns among scientists and ethicists. One significant risk surrounds high-energy physics experiments, such as those conducted at the Large Hadron Collider, LHC. These experiments aim to recreate the conditions of the early universe by smashing particles together at near-light speeds. Some theoretical models suggest that such collisions, under extreme conditions, could produce microscopic black holes. While current scientific consensus holds that these minuscule black holes would evaporate almost instantly due to Hawking radiation, the remote possibility of unforeseen consequences cannot be entirely dismissed. The failure to fully understand the behavior of these black holes could, theoretically, lead to unforeseen catastrophic scenarios. Another speculative risk involves the concept of vacuum decay. According to certain interpretations of quantum field theory, our universe exists in a false vacuum state. High-energy physics experiments might inadvertently trigger a transition to a true vacuum state, leading to a bubble of lower-energy configuration expanding at the speed of light, obliterating everything in its path. This scenario, sometimes discussed in the context of false vacuum decay, remains purely theoretical and highly speculative. The energies produced in current and foreseeable human-made experiments are minuscule compared to those required for such a transition, but the notion underscores how much we still don't know about the fundamental nature of the universe. Finally, as our technological capabilities evolve, so does our potential to interfere with cosmic bodies. Advanced space missions that involve mining asteroids or altering their trajectories to avoid potential collisions with Earth pose risks of unintended consequences. Miscalculations or unforeseen interactions could send an asteroid into a collision course with Earth, rather than diverting it. Similarly, future attempts to harness cosmic energy sources or manipulate stellar bodies could, in extreme theoretical cases, result in destabilizing gravitational or energetic balances. While these scenarios remain speculative and well within the bounds of theoretical concern, they highlight the importance of cautious and well-considered approaches to advanced scientific and technological endeavors. As our knowledge about the cosmos deepens and our capacity for manipulating cosmic forces grows, so too must our responsibility and ethical considerations in exploring and experimenting with the universe's fundamental properties. Engaging international scientific communities in dialogue and establishing rigorous safety protocols are crucial steps to mitigate such risks and ensure that our pursuits do not inadvertently unleash catastrophic consequences. The unpredictable nature of cosmic phenomena keeps scientists on edge because it underscores the vast unknowns still lurking within the universe. One of the key factors contributing to this unease is the sheer scale and complexity of the cosmos. With billions of galaxies, each containing billions of stars and an incalculable number of planets, the variety of potential cosmic events is staggering. This includes everything from supernovae and gamma-ray bursts to rogue planets and black holes. Even with advanced observational tools and theoretical models, predicting when and where these events might occur remains an immense challenge. Adding to this uncertainty is our incomplete understanding of many astrophysical processes. For example, while we have a solid grasp on the mechanisms driving supernovae, the precursors to these cataclysmic explosions can be subtle and difficult to detect from Earth. In the case of gamma-ray bursts, their transient nature means they can appear and disappear within seconds, often without leaving much trace. These phenomena release immense amounts of energy, and if they occur close enough to Earth, could have devastating effects on our planet's biosphere. The rarity but high impact of such events means that even a slight increase in the probability of their occurrence can have significant implications for our understanding of cosmic risk. The hunt for dark matter and dark energy further exemplifies the unpredictable nature of cosmic phenomena that keeps astronomers and physicists vigilant. These mysterious components make up the vast majority of the universe's mass energy content, yet their true nature eludes direct detection and understanding. Observations and experiments continuously challenge existing theories, suggesting new and sometimes contradictory paths forward. Each new piece of data carries the potential to upend established models, keeping the scientific community in a constant state of alert as they seek to unravel these cosmic mysteries. Furthermore, the dynamic and often chaotic behaviors of objects like asteroids and comets add another layer of unpredictability. Near-Earth objects, NEOs, can shift orbits due to gravitational interactions or non-gravitational forces like the Yarkovsky effect, which is caused by the way they absorb and re-radiate solar energy. These small but significant changes can be hard to track, sometimes resulting in last-minute discoveries of potential impact threats. The unpredictable and often violent nature of cosmic events, combined with our still-evolving understanding of the universe, means that astronomers, astrophysicists, and planetary scientists must remain vigilant, regularly updating models, improving observational techniques, and developing international collaborative efforts are crucial in mitigating these unpredictable cosmic threats. By staying at the cutting edge of technology and theory, scientists aim not only to protect our planet, but also to deepen our understanding of the universe's many mysteries. One of the most mysterious events ever observed in space is the phenomenon known as fast radio bursts, or FRBs. First discovered in 2007, these bursts are incredibly powerful yet brief, lasting just a few milliseconds. They emit more energy in that blink of an eye than the sun does in an entire day. For years, their origin remained a complete mystery until scientists pinpointed one source to a galaxy over 3 billion light-years away. Despite numerous detections, the exact cause of these bursts is still under significant debate. Some theories suggest they could be the result of highly magnetized neutron stars, while others propose that they might be evidence of advanced alien technology. The enigma deepens with the discovery of repeating FRBs, whereas most only flash once, adding layers of complexity to this cosmic puzzle. Equally captivating is the phenomenon known as dark matter and dark energy, entities that make up about 85% of the total mass of the universe, yet remain undetected by direct measurement. We infer their existence through their gravitational effects on visible matter, such as galaxies and galaxy clusters. Dark matter acts like an invisible scaffolding, holding galaxies together, but doesn't emit, absorb, or reflect light, making it profoundly elusive. Dark energy, on the other hand, is even more perplexing. It is believed to be responsible for the accelerated expansion of the universe, a discovery that earned the Nobel Prize in Physics in 2011. However, what dark energy actually is remains one of the biggest questions in cosmology today, pushing the boundaries of our understanding of physics and the universe itself. A sudden and intense burst of solar activity, such as a significant solar flare or a coronal mass ejection, CME, could have devastating effects on Earth. Solar flares are sudden eruptions of energy on the sun's surface caused by the tangling, crossing, or reorganizing of magnetic field lines. When these flares are powerful enough, they can release a CME, an enormous expulsion of plasma and magnetic field from the solar corona. If such a CME were to collide with Earth's magnetosphere, the consequences could be severe. For instance, the famous Carrington event of 1859, a massive geomagnetic storm, disrupted telegraph systems across Europe and North America. If a similar event occurred today, it could potentially wreak havoc on our interconnected electrical grids, satellites, and communication systems, leading to widespread power outages and communication blackouts. Beyond technological disruptions, a massive increase in solar activity could also impact our planet's climate and atmosphere. High-energy particles from the sun can damage the ozone layer, which shields Earth from harmful ultraviolet radiation. An impaired ozone layer means more UV radiation reaches Earth's surface, elevating the risk of skin cancer and other health issues. Moreover, increased solar radiation could result in variations in weather patterns and climate anomalies, making natural disasters more frequent or unpredictable. While we enjoy the warmth and light from our closest star, it's crucial to remember that a sudden and intense shift in its activity could expose Earth to a cascade of potentially catastrophic events, emphasizing the need for sophisticated monitoring and preparedness systems. Space weather, particularly solar flares and coronal mass ejections, CMEs, poses significant risks to both our technological infrastructure and human health. Solar flares are intense bursts of radiation resulting from the release of magnetic energy, and when they lash out into space, they can directly affect the Earth's ionosphere. This can lead to disruptions in high-frequency radio communications, which are crucial for airlines, maritime operations, and military activities. More alarming are CMEs, massive clouds of charged particles ejected from the sun that can travel millions of miles per hour. When these energetic particles reach Earth, they interact with our planet's magnetic field, potentially causing geomagnetic storms. Such storms can induce electric currents in power lines, transformers, and pipelines, often resulting in widespread electrical blackouts. Imagine the chaos if entire cities or even countries were plunged into darkness without power for days or weeks. The dangers extend beyond the ground to space-based infrastructure, particularly satellites. Satellites are the backbone of modern communication, GPS navigation, weather forecasting, and even financial transactions. High-energy particles from solar flares and CMEs can damage or disable these satellites, knocking out critical services we depend on daily. Furthermore, astronauts aboard the International Space Station and future deep space missions are particularly vulnerable to increased radiation levels caused by these solar events. Prolonged exposure can pose serious health risks, including acute radiation sickness, increased cancer risk, and potential harm to internal organs. Space weather, therefore, is not just a distant astronomical curiosity, it has real and immediate implications for our daily lives, necessitating vigilant monitoring and predictive modeling to mitigate its potentially catastrophic effects. An unidentified wandering celestial object, such as a rogue planet or an interstellar comet, could pose significant threats to our solar system's delicate gravitational balance. These wanderers are not bound to any star and drift through the galaxy, possibly intruding into established planetary systems. If such an object were to venture close to our solar system, its gravitational influence could perturb the orbits of planets, asteroids, and comets. Even a minor shift in the orbit of a large asteroid within the asteroid belt could set it on a collision course with Earth, potentially leading to catastrophic impacts. Additionally, a wandering celestial object passing through our solar system might interact with the Oort cloud, an extensive shell of icy bodies surrounding the outer edges of the solar system. This interaction could dislodge a multitude of comets, sending them hurtling towards the inner solar system. These comets could pose significant impact threats to Earth or other planets, much like the theorized comet or asteroid that led to the extinction of the dinosaurs approximately 65 million years ago. Moreover, the influx of such celestial debris could cause prolonged meteor showers, increasing the likelihood of destructive impacts over extended periods. Such scenarios, though rare, underscore the importance of continuous vigilance and advanced astronomical monitoring systems. Identifying and tracking these wandering objects well in advance could provide crucial time to develop potential deflection strategies or other defensive measures to mitigate their threats. It's a compelling reminder that our solar system, while seemingly tranquil, exists within a dynamic and ever-changing galaxy where unknown dangers could loom. If a massive, undetected asteroid were on a collision course with Earth, the consequences could be dire, depending on its size and impact location. An asteroid a few kilometers in diameter has the potential to cause widespread devastation on a global scale. The impact would release an enormous amount of energy, equivalent to millions of nuclear bombs detonating simultaneously. This could trigger massive earthquakes, tsunamis, and a shockwave that would obliterate everything in its immediate vicinity. The impact would eject vast quantities of dust and debris into the atmosphere, potentially blocking sunlight for months, leading to a phenomenon known as an impact winter. This could drastically reduce temperatures worldwide, collapse ecosystems, jeopardize food production, and result in mass extinctions similar to the event that wiped out the dinosaurs approximately 65 million years ago. The scenario's urgent nature is compounded by the fact that our current asteroid detection systems, though advanced, are not infallible. Smaller, more difficult to detect asteroids, or those approaching from the direction of the Sun, might evade early detection, reducing the time available to mount a response. Efforts to deflect or destroy an incoming asteroid require significant preparation and coordination. Potential strategies include nuclear detonations to alter the asteroid's trajectory, kinetic impactors to nudge it off course, or even more advanced concepts like gravitational tractors, which use a spacecraft's gravity to pull the asteroid into a different path. However, the success of such missions depends on early detection and ample lead time, underscoring the critical need for continuous monitoring and investment in asteroid detection technology. While Earth's defenses against these celestial threats are growing, the specter of an undetected asteroid remains a potent reminder of our planet's vulnerability within the cosmic arena. The growing problem of space debris, often referred to as space junk, poses a substantial and unpredictable threat to both our space infrastructure and operations on Earth. Space debris encompasses defunct satellites, spent rocket stages, fragments from collisions and explosions, and even tiny paint flecks that can travel at velocities up to 17,000 miles per hour. At such high speeds, even small debris can cause significant damage to functioning satellites, spacecraft, and the International Space Station, ISS. A collision with just a millimeter-sized object can pierce a spacecraft's hull, while larger debris could destroy satellites worth hundreds of millions of dollars or critically endanger human lives in crewed missions. One of the gravest concerns is the potential for a catastrophic chain reaction known as the Kessler syndrome. Proposed by NASA scientist Donald J. Kessler in 1978, this scenario involves a cascade of collisions that exponentially increase the number of debris fragments in orbit. Each collision generates more debris, which in turn increases the likelihood of further impacts. If such a chain reaction were to occur, it could render certain orbits extremely hazardous, making it difficult or impossible to launch satellites, communicate via spaceborne systems, or even explore space beyond our planet. The debris could also potentially re-enter the Earth's atmosphere in an uncontrolled manner, posing risks to populated areas. Addressing the unpredictability and potential catastrophe posed by space debris requires international cooperation and advanced technological solutions. Measures include tracking and cataloging known debris, devising methods to deorbit defunct satellites, and developing spacecraft shielding to withstand impacts. New technologies, such as laser-based systems or robotic space janitors, are being explored to actively remove debris from orbit. Despite these efforts, the ever-increasing volume of space traffic signifies that mitigating the risks posed by space debris will remain a crucial challenge in protecting both our space assets and terrestrial infrastructure from potentially catastrophic scenarios. The existence of advanced alien civilizations poses intriguing and potentially perilous prospects for humanity. One of the most significant threats could arise from a phenomenon often described in theoretical discussions as the Great Filter. This concept suggests that civilizations reach a certain technological threshold where their existence is either catastrophically curtailed or they ascend to a form of existence beyond our comprehension. Encountering an advanced civilization could imply that they have successfully navigated this Great Filter, but the question remains whether their intentions would be benign or hostile towards us. If these extraterrestrial beings were to perceive humanity as a threat or as simply expendable, we might face consequences ranging from technological disruption to outright annihilation. Furthermore, an advanced alien civilization could possess technologies and capabilities far beyond our own understanding, sometimes described as Clarke's third law. Any sufficiently advanced technology is indistinguishable from magic. Such civilizations might have the power to manipulate space-time, engineer planets, or even harvest energy from stars. Unwitting engagement with such entities might expose us to sophisticated forms of manipulation, including hegemonic control, enslavement using advanced AI or biotechnologies, or even ecological destruction via engineered pathogens or climatic changes. The mere detection of such a civilization could provoke global panic, not just from the fear of direct conflict, but from the potentially destabilizing effect on our socio-political structures, belief systems, and economies. Additionally, there are philosophical and ethical implications to consider. The very act of contact could shift humanity's perception of itself and its place in the cosmos. This shift could either unify us in unprecedented ways or lead to fragmentation and conflict as different groups react differently to the new reality. Some theorists argue for careful, deliberate approaches to any potential contact or detection of advanced extraterrestrial life, while others warn against the perils of broadcasting our existence indiscriminately. Regardless, encountering an advanced alien civilization remains one of the most profound and unpredictable challenges humanity could ever face. The necessity for cautious, well-considered strategies in dealing with this possibility cannot be overstated. The potential dangers of contact with hostile extraterrestrial beings are manifold and deeply unsettling. One of the most immediate threats would be the possibility of an invasion or direct attack. If an extraterrestrial civilization possesses hostile intent and advanced technology, they could deploy weaponry far beyond our current defensive capabilities. This could range from sophisticated energy weapons to kinetic bombardments, devastating cities and infrastructure with surgical precision. Given their likely superiority in technology, they could disable our communication networks, neutralize military defenses, and cause mass casualties in unprecedented ways. The sheer speed and efficiency with which they could execute an attack might give humanity little to no time to mount an effective defense or response. Beyond physical destruction, hostile extraterrestrials could engage in psychological and biological warfare. The psychological impact alone of realizing we are not alone and that our cosmic neighbors are hostile could cause widespread panic, societal breakdown, and loss of morale. On a more insidious level, they could deploy biological agents engineered to target human biology, unleashing pandemics far deadlier than anything we have encountered. These biological agents could be designed to spread rapidly and elude medical intervention, leading to large-scale loss of life and long-term genetic impacts on survivors. Moreover, hostile extraterrestrials might not need to conquer through brute force. They could impose their dominance through technological subjugation. By crippling our digital infrastructure, they could control our communications, financial systems, and even critical utilities like water and power. Advanced forms of artificial intelligence and cyber warfare could turn our own technology against us. They might even manipulate our climate or ecosystems to create inhospitable conditions, effectively cornering humanity into submission without direct confrontation. The ethical and existential dilemmas posed by such contact are also profound. Should we attempt to negotiate or resist? What sacrifices would be necessary for survival, and would they compromise our humanity? While it remains speculative, the potential dangers of contact with hostile extraterrestrial beings serve as a compelling argument for caution in our search for intelligent life, urging us to balance our curiosity with a sober assessment of the possible risks. The unknown intentions of possible alien life forms stir profound fear, largely because of the uncertainty and potential for the unknown. When faced with a significant unknown, human beings often project their deepest anxieties onto the void, creating scenarios that range from benign curiosity to existential dread. The mere possibility that an advanced extraterrestrial civilization could be aware of us brings to the fore questions about their motives and actions. Are they explorers, scientists, or conquerors? Without clear answers, the spectrum of possibilities can induce a state of collective apprehension. One source of fear is the dislocation of humanity's self-understanding. For millennia, we have considered ourselves the dominant intelligent life forms on Earth, if not the universe. The discovery of alien life with unknown intentions would challenge this notion, potentially relegating us to a lesser role in the cosmic order. Such a shift could unsettle our cultural, religious, and philosophical foundations, leading to widespread existential angst. The fear of becoming subordinate to, or being utterly obliterated by, a more advanced species brings to mind historical parallels of indigenous populations encountering colonizing forces, often with devastating consequences. Additionally, the potential technological disparity heightens this fear. An advanced alien civilization would likely possess capabilities far beyond our current understanding, potentially rendering us vulnerable to unpredictable interventions. They could monitor or manipulate us without our knowledge, undermining our sense of autonomy and security. The possibility of psychological manipulation, technological enslavement, or covert biological experimentation fuels a fear rooted in our lack of control over our destiny. The fear of the unknown intentions of alien life forms also taps into deeper primal fears embodied in our mythologies and narratives. From ancient texts to modern sci-fi, stories of unknown entities coming from the skies have often been linked with themes of invasion, abduction, and apocalypse. These cultural archetypes reinforce our collective apprehension, magnifying the emotional and psychological impact of contemplating alien intentions. The fear generated by the unknown intentions of possible alien life forms is a complex amalgamation of existential unease, historical precedent, and deeply ingrained cultural narratives, reminding us of both our vulnerability and curiosity in facing the mysteries of the cosmos. The Fermi paradox, which questions why we have not yet encountered evidence of extraterrestrial civilizations despite the vastness of the universe, holds profound implications for the potential danger from aliens. One unsettling hypothesis that stems from this paradox is the idea that advanced civilizations may tend to self-destruct before they can make their presence known to others. This hypothesis suggests that the development of technologies capable of interstellar communication or travel may coincidentally harbor the seeds of that civilization's destruction, such as nuclear weapons, climate change, or other cataclysmic technologies. If this self-destruction theory is accurate, it implies that our own civilization might be on a similar precipice, highlighting the importance of managing our technological advancements responsibly to avoid annihilation. Another possible implication is the dark forest hypothesis, which postulates that advanced civilizations keep silent and hidden to avoid detection. In this scenario, civilizations might assume that any contact with extraterrestrial life is inherently dangerous, leading them to stay silent to protect themselves from potentially hostile entities. If this hypothesis holds, it suggests that any alien civilization we might encounter could perceive us as a threat and act preemptively to neutralize that threat. The notion of space as a dark forest, where every noise and signal could attract predatory attention, adds a layer of cautiousness to our attempts at seeking out extraterrestrial intelligence. It serves as a stark warning against aggressive or hasty attempts to communicate our presence to the cosmos. The Fermi paradox also prompts reflection on our own readiness for contact. If advanced civilizations avoided contact or concealed their existence to evade danger or due to ethical considerations we cannot fathom, we must question our preparedness to engage responsibly. Our response to contact, whether benign or otherwise, would need to be measured and considerate, accounting not only for technological and defense implications, but also for ethical, philosophical, and societal impacts. The Fermi paradox underscores the potential risks involved in seeking out extraterrestrial intelligence and highlights the dual-edged nature of such an endeavor. It pushes us to contemplate our own civilization's trajectory and the precautions necessary to ensure that our quest for knowledge does not jeopardize our survival. The paradox encourages a blend of scientific inquiry with caution, reminding us that the silence of the cosmos might be a reflection of inherent risks known all too well by those who have ventured before us. The technology of an advanced alien civilization could far surpass our own in ways that pose significant existential risks to humanity. Imagine a civilization that has had millions or even billions of years more technological development than us. Such a civilization could have mastered energy manipulation at scales we can scarcely imagine, such as harnessing the energy output of entire stars with Dyson spheres or controlling quantum-level phenomena to create matter from pure energy. Their mastery of physics, likely encompassing principles we have yet to discover, could render our most advanced technologies as primitive as stone tools. One possible existential risk is through the deployment of von Neumann probes, self-replicating machines capable of exponential reproduction using local resources. Once set into motion, these probes could convert entire planetary systems, including ours, into raw materials for further replication, thereby erasing any indigenous life forms in their path. The rapid, uncontrolled proliferation of such technology, if weaponized or simply following a prime directive to propagate, represents a scenario where human intervention would be futile. Another chilling prospect is the potential use of advanced nanotechnology. Alien civilizations could deploy nanobots capable of self-replication and reconfiguration, far surpassing our understanding of molecular engineering. These nanobots could be used to dismantle biological and synthetic matter on Earth at a molecular level, effectively disintegrating everything from living organisms to our most robust constructions. Known as a grey goo scenario, this represents a level of threat that could decompose our planet's biosphere to raw, inorganic matter, leaving Earth a barren wasteland. Moreover, advanced alien civilizations might possess the capability for real-time manipulation of space-time. Weaponizing such control could allow them to create black holes, manipulate gravitational waves, or induce destructive cosmic phenomena like gamma-ray bursts directed toward Earth. The implications of such power are staggering, as they could end all life on our planet instantaneously and from incomprehensible distances. The psychological and societal impacts of encountering such superior technology would also be profound. Our geopolitical, economic, and cultural systems could collapse under the realization of our relative insignificance and powerlessness, leading to existential despair, widespread panic, and potentially violent societal upheavals. In conclusion, while the search for extraterrestrial intelligence is driven by a thirst for knowledge and a sense of cosmic kinship, it is essential to consider the risks posed by encountering technologies that far exceed our own. These technologies could not only outmatch us in every conceivable way, but also possess the capabilities to annihilate our civilization or co-opt our planet for purposes beyond our comprehension. Thus, the potential discovery of advanced extraterrestrial life necessitates an approach balanced with profound caution and preparedness for scenarios that challenge our very existence. If extraterrestrial life were to perceive humanity as a threat and decide to act accordingly, the ramifications could be catastrophic on both an immediate and existential level. An advanced alien civilization, seeing our rapid technological advancements and increasing ability to explore the cosmos, might preemptively strike to neutralize what they perceive as a potential future rival. The methods they might employ could vary greatly depending on their technological capabilities, potentially rendering our defenses utterly ineffective. One of the first signs of such an existential threat could be a targeted extermination strategy, leveraging their superior knowledge and technology to ensure rapid and complete eradication. This could take the form of deploying advanced weaponry, such as directed energy weapons that could incinerate cities, EMP pulses to disable all electronic devices, or even more exotic technologies like antimatter bombs. These preemptive strikes would likely be designed to cripple human civilization quickly and decisively, minimizing the risk of any prolonged resistance or counterattack. Another plausible scenario involves the use of biological warfare. Advanced extraterrestrial beings could design pathogens tailored to human biology, highly infectious and resistant to our medical interventions. Such bioweapons could spread rapidly, causing mass casualties and societal collapse. Given their advanced knowledge of genetics, these pathogens could have multiple vectors and incubation periods, making them extraordinarily difficult to contain. This approach would be particularly insidious, achieving their goal without the need for direct confrontation or visible destruction. They might also harness environmental manipulation to make Earth uninhabitable, employing techniques such as inducing climate extremes, altering the composition of our atmosphere, or causing geological disruptions like earthquakes and volcanic eruptions. Such a strategy would not only decimate human populations, but also disrupt ecosystems, ensuring long-term uninhabitability and effectively sterilizing the planet against future threats. Additionally, extraterrestrials could opt for psychological and cyber warfare, undermining human societies from within. They could infiltrate and distort our communication networks, spread disinformation, and manipulate global economies to foster distrust, paranoia, and conflict among human nations. The resulting chaos and fragmentation could weaken our global cohesion and resilience, making humanity easier to conquer or control without ever firing a shot. Moreover, their assessment of humanity as a threat might stem from observing human behavior, our history of warfare, environmental exploitation, and social inequalities. To them, these traits might suggest that we are too volatile or morally unfit to join a broader cosmic community, prompting them to act in what they perceive as the galaxy's best interest. In light of these possibilities, the notion of extraterrestrials perceiving humanity as a threat compels us to adopt a more cautious and humble approach in our cosmic endeavors. While the search for extraterrestrial life inspires our imagination and fuels scientific curiosity, it also necessitates a profound understanding of the potential risks involved. Preparing for such eventualities requires not only advanced technological defenses, but also sophisticated diplomatic strategies, should we ever need to communicate our intentions and negotiate with beings far beyond our comprehension. Considering our current understanding of the universe, an alien invasion could unfold in numerous ways, each profoundly shaped by the level of technological advancement and strategic thinking of the extraterrestrial invaders. Given the vast distances involved in interstellar travel, it's likely that any civilization capable of reaching Earth would possess technologies far superior to our own, making their strategies efficient and potentially devastating. One plausible scenario is a surprise attack utilizing advanced reconnaissance capabilities. Well before any visible signs of their presence, extraterrestrials could deploy stealthy, unmanned probes to gather intelligence on Earth's defenses, resources, and vulnerabilities. These probes could remain undetected, relaying critical data back to their origin civilization and allowing for meticulous planning. In this phase, they might also disrupt or hack our satellite communications and global positioning systems, impairing our ability to respond effectively to an invasion. The initial assault could begin with a cyber and electronic warfare campaign, targeting our digital infrastructure to sow confusion and disarray. Power grids, telecommunications networks, and financial systems could be crippled, rendering modern societies ineffective and chaotic. Simultaneously, they might unleash highly advanced electromagnetic pulse (EMP) weapons to shut down all electronic devices over wide areas, effectively paralyzing military and civilian capabilities. Following the initial destabilization, the physical invasion might commence with highly coordinated strikes using energy weapons, precision-guided munitions, or even orbital bombardments. These attacks could target major military installations, communication hubs, and infrastructure critical for human survival, such as dams, power stations, and transportation networks. Their aim would be to neutralize any organized resistance quickly and decisively. Given their likely technological superiority, these extraterrestrials might deploy autonomous drones and robotic forces to carry out ground operations, minimizing their risk and ensuring efficiency. These machines could be equipped with advanced AI, making them incredibly difficult to combat using traditional human military tactics. The extraterrestrials might also use advanced materials and shield technologies that render their forces impervious to our conventional weaponry. If biological or psychological warfare is part of their strategy, they might introduce tailored pathogens engineered to disrupt human biology or deploy technology capable of inducing mass panic and fear through psychological manipulation. These methods would exponentially increase chaos and reduce resistance, making it easier for them to establish control. Once initial objectives are secured, the extraterrestrial invaders could implement occupation strategies designed to exploit Earth's resources while maintaining control over the human population. They might use advanced surveillance to monitor movements and communications, ensuring compliance and swiftly quelling any insurgency. Enforced indoctrination or assimilation programs could be initiated to align human behavior with their strategic goals, potentially reshaping our very way of life. Underpinning these invasion scenarios is the assumption that their motives could range from resource acquisition and colonization to preemptive self-defense, shaped by their assessment of humanity as a threat. Regardless of their reasons, an alien invasion would likely be swift, methodical, and devastating, leveraging their advanced technology to overcome our defenses and drastically alter life as we know it. While the specifics of how an alien invasion might unfold are inherently speculative, our understanding of the universe and human history provides a framework for imagining the profound implications such an event would have on humanity, emphasizing the need for vigilance and preparedness even as we extend our gaze into the cosmos. The risks of sending messages to potential alien civilizations are rooted in the fundamental unpredictability of alien intentions and the asymmetrical technological capabilities they may possess. One of the most significant dangers is the possibility of attracting the attention of a hostile or exploitative civilization. If an advanced extraterrestrial species were to receive our message and perceive humanity as a potential threat, rival, or resource, they might choose to act preemptively, potentially leading to scenarios of invasion, exploitation, or even annihilation. This scenario aligns with the dark forest hypothesis, which posits that civilizations remain silent to avoid detection and potential eradication by more advanced and aggressive entities. Increased visibility could also expose us to civilizations that, while not actively hostile, may see Earth as a prime candidate for colonization or resource extraction, driven by their own needs or expansionist tendencies. The historical precedent of more technologically advanced societies encountering less advanced ones on Earth often involved exploitation, domination, and other detrimental outcomes for the latter. Advanced extraterrestrial civilizations might employ highly efficient extraction methods that could disrupt our ecosystems, deplete natural resources, or fundamentally alter the environment, creating existential threats to our way of life and survival. Moreover, the act of messaging extraterrestrial civilizations could inadvertently reveal a wealth of information about our technological, cultural, and biological makeup, providing them with valuable intelligence. This could make it easier for them to devise strategies to manipulate or control humanity. Detailed knowledge of our biochemistry, for instance, could lead them to develop specific pathogens or other biological agents capable of debilitating or controlling human populations, facilitating subjugation with minimal effort on their part. Even if extraterrestrial civilizations are benign, cultural contamination and the imbalance in technological advancements could have profound implications. Sudden exposure to advanced knowledge and technologies might disrupt societal structures, economies, and belief systems, potentially leading to chaos and destabilization. The psychological impact of encountering an advanced alien civilization would be immense, potentially causing existential crises, mass hysteria, or widespread unrest. Finally, there's the ethical dilemma of making such contact decisions. The long-term consequences of revealing our presence to the cosmos are unknown and potentially irreversible. It raises questions about who has the authority to make such decisions on behalf of humanity and the potential fallout on future generations who will have to live with the consequences. Given these risks, there are compelling arguments for adopting a more cautious, contemplative approach to messaging extraterrestrial civilizations, one that balances the thirst for knowledge and contact with the prudence required to protect humanity from unforeseen and potentially catastrophic outcomes. The possibility of bioengineered extraterrestrial diseases poses a profound and multifaceted threat to Earth, largely because such pathogens could be specifically designed to exploit human vulnerabilities at a biological level. An advanced extraterrestrial civilization with sophisticated knowledge of genetics and biotechnology could create diseases tailored to bypass or overwhelm our immune systems, leading to rapid and uncontrollable outbreaks. Unlike naturally occurring pathogens, these bioengineered diseases could be optimized for high transmission rates, resistance to treatment, and severe pathogenicity, making them extraordinarily difficult to manage with current medical technology. Such a scenario could be particularly devastating if the bioengineered disease were to target specific aspects of human biology or physiology. For example, an engineered virus might exploit receptors that are common across various human tissues, making it capable of affecting multiple organ systems simultaneously. This could result in a range of debilitating symptoms that overwhelm healthcare infrastructures, leading to high mortality rates and widespread social disruption. Traditional methods of disease control, such as quarantine or vaccination, could prove ineffective if the pathogen were designed to evade or neutralize these measures. The introduction of an extraterrestrial pathogen could also have significant ecological impacts. A well-designed bioengineered disease might not only affect humans but could spread to other species, disrupting ecosystems and food chains. The loss of key species could have cascading effects on biodiversity and environmental stability, compounding the crisis and making recovery even more challenging. Furthermore, a pathogen that jumps between species could also facilitate the evolution of new variants, potentially leading to a series of pandemics with varying characteristics. Moreover, the psychological and societal impacts of an extraterrestrial bioengineered disease would be profound. The sudden appearance of a highly lethal pathogen from an alien source could incite global panic, leading to social unrest and breakdown of trust in institutions. Governmental and international bodies might struggle to coordinate an effective response, and the ensuing chaos could exacerbate the spread of the disease. People might resort to extreme measures out of fear and desperation, further destabilizing societies. In a broader context, the threat of bioengineered extraterrestrial diseases highlights the need for advanced biodefense strategies and international cooperation. Developing robust surveillance systems to detect unusual outbreaks early, investing in rapid response medical research capabilities, and creating comprehensive pandemic preparedness plans are crucial steps. Additionally, the possibility of bioengineered diseases reinforces the importance of cautious interaction with potential extraterrestrial entities and the need for protocols to mitigate risks when sending messages or receiving unknown signals from space. Ultimately, while the idea of encountering alien life is both thrilling and intellectually stimulating, the potential risks associated with bioengineered extraterrestrial diseases serve as a sobering reminder of the complexities and dangers inherent in such encounters. It underscores the necessity for balanced, well-considered approaches in our efforts to explore and understand the cosmos, ensuring that our quest for knowledge does not inadvertently invite catastrophic outcomes. In the vast expanse of the cosmos, the idea of alien life has long fascinated and terrified humanity. One scenario where extraterrestrial beings might accidentally harm our planet involves their attempts at exploration or resource extraction. Aliens, driven by a need to understand or utilize Earth, could introduce non-native microorganisms to our biosphere. While seemingly innocuous, even a single bacteria or virus from an alien world could wreak havoc, similar to how invasive species on Earth disrupt local ecosystems. Additionally, mining operations by advanced extraterrestrial civilizations might inadvertently cause massive environmental damage. Their technologies, although far superior, might interact unpredictably with our planet's geology or atmosphere, triggering unintended consequences such as earthquakes or toxic pollution. On the other hand, intentional harm could stem from interstellar conflict or a desire to preemptively neutralize potential threats. If extraterrestrial civilizations perceive humanity as a future rival or a dangerous species, they could deploy advanced weaponry or bioengineered pathogens to destabilize or destroy our civilization. Consider the potential deployment of antimatter weapons, which could cause catastrophic energy releases on a planetary scale, dwarfing the most powerful nuclear weapons in human history. Another troubling possibility involves psychological manipulation, where extraterrestrial forces use advanced mind control or disinformation tactics to sow discord and chaos among Earth's population, fracturing societies from within and leading to self-destruction without a single shot fired. These scenarios, though speculative, remind us of the profound uncertainties and risks that accompany the search for cosmic neighbors. The end of the universe isn't just a topic for science fiction, it's a subject of serious scientific inquiry, with several plausible scenarios, each with its own blend of awe and terror. One of the most discussed theories is the heat death of the universe. This scenario is grounded in the second law of thermodynamics, which suggests that as the universe continues to expand, it will gradually reach a state of maximum entropy. In simpler terms, the cosmos will cool down as stars burn out and no new ones are born. Over eons, galaxies will dim, planets will freeze, and black holes will evaporate, leaving a dark, cold expanse where all activity ceases, and time seems to stretch indefinitely. While this end is relatively peaceful, the sheer emptiness and endless dark chill evoke a profound existential dread. In stark contrast, the Big Rip posits a more violent conclusion to all existence. According to this hypothesis, the mysterious dark energy that is driving the accelerated expansion of the universe could eventually grow stronger. If dark energy's influence continues to increase, it will not only keep pushing galaxies apart, but also tear apart gravitationally bound systems like galaxy clusters, solar systems, and eventually even atoms. Picture the fabric of space-time being rent asunder at an ever-accelerating pace until, in a final crescendo of cosmic ruination, everything, including fundamental particles, dissolves into an inconceivably chaotic state within seconds. This scenario is terrifying in its absolute explosive finality. Another cataclysmic possibility is the Big Crunch, a kind of cosmic collapse. If the universe's density were high enough to counteract its expansion, gravity could halt and reverse this process, causing all matter and space-time to collapse inward. This would culminate in an immensely dense and hot state, potentially leading to either a final singularity or a rebirth into a new universe through a hypothetical Big Bounce. The thought of an inexorable collapse, compressing all matter to a single infinitely dense point akin to a black hole's singularity, is profoundly unsettling. Each of these potential endings, whether a cold, desolate fade to black, a sudden tear through the very fabric of reality, or a harrowing collapse into oblivion, underscores the delicate balance and colossal forces at play in our universe. The Big Rip presents one of the most catastrophic visions for the end of the universe, driven by the enigmatic force known as dark energy. Dark energy, which constitutes approximately 70% of the universe's total energy density, is responsible for the observed accelerated expansion of the cosmos. The central idea behind the Big Rip is that this acceleration will not remain constant, but rather will increase over time. If the repulsive force of dark energy continues to grow stronger, it will eventually overcome all other fundamental forces, leading to a sequence of increasingly violent events. Initially, the Big Rip begins subtly. Galactic clusters, which currently hold together under the pull of gravity, will start to drift apart as the space between them expands more rapidly. Next, within individual galaxies, stars will begin to lose their gravitational grip on one another, scattering into the expanding void. As the process escalates, solar systems will be torn asunder. Planets might be ripped from their orbits and sent hurtling into the darkness. The horrifying escalation continues down to the atomic level. The very atoms that constitute matter will find the space between their nuclei and electrons expanding uncontrollably. ultimately disassembling atoms into subatomic particles. What makes the Big Rip uniquely terrifying is its relentless progression towards cosmic disintegration. While other end-of-universe scenarios like the heat death or Big Crunch play out over billions or trillions of years, the final moments of the Big Rip would occur over a relatively brief, devastating time span. The closer the universe gets to this hypothetical end, the faster and more violently everything falls apart, culminating in a second of unimaginable chaos where molecules, atoms, and even subatomic particles are torn asunder. In this last, dizzying instant, the universe as we know it fractures into an incoherent void, leaving behind an unrecognizable expanse devoid of any structure or form, a haunting reminder of the inexorable power of dark energy. Heat death, also known as the Big Freeze, is a theorized final state of the universe where it reaches maximum entropy and can no longer sustain thermodynamic processes. This scenario is rooted in fundamental principles of thermodynamics, particularly the second law, which states that entropy, or the measure of disorder in a system, always increases over time. As the universe continues to expand, it gradually disperses energy across an ever-growing volume of space. Stars will exhaust their nuclear fuel, galaxies will become ghostly clusters, and no significant sources of heat or light will remain. In this bleak future, the universe would be characterized by a uniform temperature close to absolute zero. All stars would have long since ceased to shine, turning into white dwarfs, neutron stars, or black holes. Even these remnants would eventually lose energy through processes like Hawking radiation, whereby black holes slowly evaporate over unimaginably long timescales. With no energy differentials to drive physical processes or support life, all forms of movement, chemical reactions, and biological functions cease. Planets become cold, inert masses, left drifting in an insufferable cold void. The implications of heat death are profound and deeply chilling, both literally and metaphorically. Without usable energy, the universe would become an endless expanse of darkness. The once vibrant cosmological tapestry of galaxies, stars, and planets would dissolve into a homogeneous sea of subatomic particles, spread thinly across an ever-expanding space. This state lacks any potential for complexity, structure, or change, locking the universe in a static fate. It represents a future of eternal stasis, where time becomes almost meaningless, and the cosmos enters an infinite silent stillness. For those pondering the fate of existence, the heat death of the universe evokes a sense of ultimate finality and profound isolation, encapsulating the inexorable march towards universal equilibrium. The Big Crunch posits a dramatic cyclical end to the universe, where the relentless expansion driven by the Big Bang is eventually reversed by the force of gravity. In this scenario, the fate of the universe hinges on its overall density, the critical factor that determines whether gravity can overcome the expansion. If the universe contains enough mass, including dark matter and ordinary matter, the gravitational pull would eventually halt the expansion and begin to contract it all back inwards. Initially, this contraction would be slow and almost imperceptible, drawing galaxies closer together over billions of years. As the process continues, galaxies would collide and merge, and the night sky would grow increasingly chaotic with the intensified gravitational interactions. Stars, planets, and other celestial bodies would get drawn into an ever-tightening cosmic knot. The cosmic background radiation, which serves as a remnant heat from the Big Bang, would grow hotter as the universe contracts, reversing the cooling trend observed today. As the universe continues to compress, the distances between all forms of matter shrink dramatically, leading to increasingly catastrophic consequences. Matter would get squeezed into incredibly dense states, and temperatures would soar to unimaginable levels. The fabric of spacetime itself would warp under the immense gravitational forces, causing all existing structures to break down. At some point, the density and temperature would reach such extremes that atomic nuclei are crushed together, and even elementary particles might cease to exist in their recognizable forms. Finally, all this accumulated matter and energy would converge into a single point, akin to a singularity, much like the state hypothesized to have existed before the Big Bang. This ultimate gravitational collapse could either signify the absolute end of the current universe or potentially ignite a new Big Bang, giving rise to a new cycle of cosmic birth, expansion, and eventual collapse, a concept known as the Big Bounce. The Big Crunch, with its cataclysmic finality, offers an awe-inspiring, albeit harrowing vision of the universe returning to a single, infinitely dense and hot state, encapsulating a cosmic cycle of death and rebirth. False vacuum decay presents one of the most unsettling and sudden ways the universe could meet its demise, rooted in the peculiar aspects of quantum field theory. The concept starts with the idea that our universe might currently reside in a false vacuum state. In quantum field theory, a vacuum is not merely empty space, but a field with the lowest possible energy. However, what we think is the lowest energy state, the false vacuum, might actually be a local minimum, akin to sitting in a valley surrounded by higher peaks, while a true vacuum would be the absolute lowest energy state, like a deeper valley hidden behind one of those peaks. If this is the case, a sufficiently energetic event such as quantum tunneling could suddenly cause a transition to the true vacuum state. Imagine a small bubble forming where the false vacuum state transitions to the true vacuum. This bubble would rapidly expand at the speed of light, reconfiguring the laws of physics as it goes. Within this bubble, fundamental constants and forces might change, leading to the instant annihilation of any matter and structures it encompasses. The serene predictability of everyday physics would be shattered, leading to devastating transformations as the bubble of true vacuum envelops everything in its path. The implications of false vacuum decay are profoundly unsettling because, given its nature, there would be no warning or sign heralding the end. The bubble would expand so fast that it would utterly consume the universe without any prior notice, leaving no time to react or adapt. Every proton, neutron, and electron, down to the very quarks and gluons that compose them, might cease to exist in recognizable forms, erased from existence in a cosmological blink. The serene, stable reality we take for granted would dissolve into an entirely different state that defies comprehension, governed by unfamiliar physics. The unpredictability and immediacy of false vacuum decay add a layer of existential anxiety to our understanding of the universe. Unlike the gradual unfolding of events in scenarios like heat death or the Big Crunch, false vacuum decay offers a stark reminder of the universe's inherent uncertainties and the potential for abrupt cosmic-scale transformations. The realm of quantum mechanics is fraught with unpredictability, and certain quantum events could, in theory, trigger the end of the universe in sudden and unexpected ways. One particularly chilling idea is that of quantum tunneling, where particles move through energy barriers that would be insurmountable according to classical physics. In the context of the universe, quantum tunneling could instigate processes like false vacuum decay, where our universe transitions from a metastable false vacuum state to a more stable true vacuum state. This transition would catalyze a chain reaction, creating a bubble of true vacuum that rapidly expands at the speed of light, obliterating everything in its path and fundamentally altering physical constants. Another potential quantum event that could usher in cosmic catastrophe is vacuum instability. If the Higgs field, which gives particles their mass, is not in its lowest energy state, it could spontaneously decay to a more stable state. This decay would unleash a tremendous amount of energy, disrupting the fabric of space-time itself. Such an event, although statistically unlikely, could transform the very nature of matter and energy, effectively rewriting the rulebook of the universe and dissolving existing structures in an instant. Quantum fluctuations can also play havoc on a grand scale. Tiny, spontaneous variations in energy levels can have significant impacts when magnified by cosmic forces. For instance, a significant fluctuation could create a micro-black hole, which might grow by accreting surrounding matter. If such a black hole were to escape detection and continue to consume matter unchecked, it could become a significant threat. While these scenarios remain within the realm of theoretical speculation, they underscore the inherent unpredictability of quantum mechanics, where even minuscule changes can lead to dramatic outcomes over time. These quantum events share one unsettling feature: their unpredictability. Unlike the slow march towards heat death or the gradual contraction of the Big Crunch, these quantum-triggered apocalypses could happen at any time without warning. The seemingly tranquil, stable universe we inhabit is balanced on a precarious edge, where below the surface, quantum processes could unleash forces capable of tearing apart the very fabric of existence. This inherent uncertainty adds a layer of profound existential contemplation. highlighting the sheer unpredictability and fragility of our cosmic home. The ultimate fate of black holes in the distant future is governed by a process first theorized by physicist Stephen Hawking, known as Hawking radiation. According to this theory, black holes are not entirely black, but emit tiny amounts of thermal radiation due to quantum effects near their event horizons. This is an incredibly slow process, as it depends on the mass of the black hole. The more massive the black hole, the less radiation it emits. However, over incredibly long timescales, even the mightiest black holes will eventually lose mass and energy through Hawking radiation. In the grand cosmological timeline, the evaporation of black holes is a protracted affair. Supermassive black holes, like the ones found at the centers of galaxies, are expected to last for an astonishingly long time, on the order of 10 to the 100th power years, far longer than the current age of the universe. As they slowly emit Hawking radiation, they will gradually shrink, their event horizons getting smaller. The radiation process accelerates toward the end, with the black hole emitting more and more energy as it loses mass, finally culminating in an explosive burst of radiation that disperses its remaining mass energy into the surrounding space. Once the cosmic scales tip and all black holes have evaporated, the universe will be a vastly different place. Without black holes, there would be no large gravitational anchors holding matter together. The cosmos would primarily consist of a sparse distribution of subatomic particles and low-energy photons, headed toward a state defined by maximum entropy. This scenario fits within the broader concept of heat death, where the universe approaches thermodynamic equilibrium and, consequently, a state of no thermodynamic free energy to sustain motion or life, resulting in a cold, dark, and quiet expanse. The ultimate fate of black holes, as envisaged by Hawking radiation, underscores the inexorable march toward cosmic simplicity. These once dominant celestial titans, capable of consuming stars and shaping galaxies, will eventually radiate away into nothingness, leaving behind a universe devoid of the dramatic gravitational interactions that marked its earlier epochs. The end of black holes is a profound reminder of the universe's relentless progression towards entropy, where even the most powerful and enigmatic objects cannot escape the ultimate decay. The expansion of the universe, a cornerstone of modern cosmology, leads to a future where galaxies become increasingly isolated and lonely. This cosmic isolation results from the accelerated expansion driven by dark energy, a mysterious force constituting about 70% of the universe's total energy density. Since its discovery, dark energy has been observed to drive galaxies apart at an ever-increasing rate. In the distant future, this relentless expansion will stretch the fabric of space-time to such an extent that even gravitationally bound structures, such as galaxy clusters, may drift away from each other. As galaxies recede from one another, the observable universe for any given galaxy will shrink. For inhabitants of a future galaxy, other galaxies will appear to fade away, their light redshifted out of existence beyond the visible spectrum. This means that distant galaxies will eventually move beyond the cosmic horizon, the limit beyond which objects disappear from view because they are traveling away faster than the speed of light due to the expansion of space itself. In such a future, an observer in any galaxy would see fewer and fewer neighboring galaxies, leading to a stark isolation. This scenario implies a universe that becomes increasingly silent and desolate. Star formation will dwindle as intergalactic gas is no longer replenished through galaxy mergers. Existing stars will age and die, turning into cold remnants like white dwarfs or neutron stars. Over 100 billion years, galaxies themselves may become red and dead, populated solely by old stars as new stars cease to form. The night skies of future civilizational astronomers will grow darker and lonelier, devoid of the dazzling array of galaxies we can see today. Ultimately, the accelerated expansion leads to a profound sense of cosmic loneliness. As galaxies become unreachable and the universe's grand structures dissolve into the void, the remaining islands of matter, our galaxy among them, will be left in a vast, dark cosmos. This portrays an isolating fate, not just in terms of physical distance, but also in terms of the loss of connectivity and interaction that currently define the dynamic, vibrant universe. The inexorable expansion driven by dark energy ensures that, over unimaginable timescales, the cosmos will become an increasingly empty stage, where each galaxy experiences its own solitary existence amidst an ever-growing void. The experience of life at the edge of the universe's end, whether it be in the context of heat death, the Big Rip, or another cataclysmic event, would be profoundly different from life as we know it today. As the universe approaches these terminal states, the fundamental conditions that sustain life would deteriorate drastically, imposing a grim and surreal existence. In the scenario of heat death, the universe would have expanded to such a degree that temperatures approach absolute zero. Stars would have burned out long ago, leaving behind only cold, dark remnants like white dwarfs, neutron stars, and black holes slowly evaporating through Hawking radiation. The cosmic background radiation, the afterglow of the Big Bang, would also fade, reaching levels indistinguishable from absolute darkness. Any form of life that could somehow persist would face extremely limited resources, with no new energy inputs to sustain metabolic processes. Some speculative forms of life might adapt to harness the residual heat from dying stars or the occasional quantum fluctuations, but these existences would be on the very brink of survivability, eking out sustenance from the last vestiges of available energy. If the universe is headed toward a Big Rip, life in the final moments would encounter a universe tearing apart at every conceivable scale. Initially, galaxies would separate, followed by solar systems disintegrating as gravitational bonds are overwhelmed. Closer to the end, planets, including any habitats they may have, would be ripped away from their stars. Atomic bonds within molecules, even down to fundamental particles, would succumb. Life, in any form, would experience increasingly chaotic and catastrophic forces. A civilization might attempt to brace against this reality, developing technological means to stay cohesive longer, but eventually, even their best efforts would be for naught. Reality would dissolve in a violent frenzy of disintegration, and any consciousness within it would be obliterated as space-time itself is shredded. At the edge of the universe's end, whether through thermodynamic decay or violent cosmic destruction, any remaining life forms would face extreme limits on survival. The environment would be inhospitable on an unprecedented scale, outside the bounds of current human comprehension. This cosmic solitude and fragmentation, coupled with the relentless march toward disorder and dissolution, would define a universe where life, if it persists at all, does so in constant struggle against the overwhelming forces of an ending cosmos. The experience would be one of perilous existence, a poignant testament to the resilience and fragility of life confronting the grandeur and finality of cosmic evolution. Contemplating the various end-of-universe scenarios underscores the extraordinary fragility of humanity's existence. Each theoretical cosmic demise, be it heat death, the Big Rip, or quantum events like false vacuum decay, places the human condition and all life on Earth within an awe-inspiring yet precarious framework of universal forces and timescales. First, consider the heat death scenario. This gradual fading into thermodynamic equilibrium starkly highlights humanity's reliance on a delicate balance of energy and thermodynamic processes. As our current era enjoys the benefits of stellar warmth, the eventual cooling of the universe would make sustaining life as we know it impossible. The specter of a universe that slowly deserts its capacity for heat and light, transitioning into a dark, cold void, accentuates the temporary and fleeting nature of our ecological niche. The Big Rip scenario adds a terrifying immediacy to this sense of fragility. Here, the relentless expansion of the universe driven by dark energy doesn't just push galaxies apart, but eventually sieves down to the very atoms that constitute matter. Humans, our homes, our planet, and the Milky Way itself would all be shredded by this overpowering force. The notion that cosmic expansion could crescendo into such a violent end casts human existence as profoundly vulnerable to forces beyond our control, operating on scales that dwarf any of our achievements. Quantum events like false vacuum decay compound this anxiety with an element of unpredictable cataclysm. The potential for a sudden quantum transition to a lower energy state, catalyzing an unstoppable wave of annihilation that alters the very fabric of physics, suggests that even our understanding of the universe's fundamental stability is tentative. This scenario showcases how, despite our technological advances and scientific knowledge, Humanity hangs by a thread over a chasm of quantum uncertainty. All these potential ends of the universe make humanity's existence appear unimaginably fragile and transient. Our lives, civilizations, and collective achievements are fleeting flickers against the backdrop of vast cosmic timelines and forces. This perspective invites a profound humility and appreciation for the relatively stable conditions we currently enjoy. It also impels a deeper reflection on our place in the universe, not just as consumers of its resources, but as temporary witnesses to its grandeur and participants in its unfolding story, reminding us of the precious and ephemeral gift that is life. The vacuum of space, with its extreme conditions, poses immediate and serious threats to human life. Unlike the relatively hospitable environment on Earth, space is an unforgiving expanse where the absence of atmospheric pressure and breathable air, extreme temperatures, and high levels of radiation all conspire to perilously challenge human survival. First and foremost, the lack of atmospheric pressure in space is a severe hazard. Human bodies are adapted to the pressure of Earth's atmosphere, which keeps bodily fluids in a stable, liquid state. In the vacuum of space, this pressure ceases to exist. If an unprotected human were suddenly exposed to space, the pressure differential would cause the water and other fluids in the body to vaporize and expand. This phenomenon, known as ebulism, could cause tissues to swell and blood to boil while still inside the circulatory system. Within seconds, consciousness would be lost due to rapid deoxygenation of the blood, and without intervention, death would quickly follow. Moreover, space offers no protection from the harsh extremes of temperature. Objects in direct sunlight can be heated to over 250 degrees Fahrenheit, around 120 degrees Celsius, while those in shadow can plunge to minus 250 degrees Fahrenheit, around minus 160 degrees Celsius. Without the buffering effects of an atmosphere, human tissues would be subjected to these severe temperature swings, posing risks of both hypothermia and hypothermia. This threat would be immediate and acute, as human bodies lack the inherent capacity to handle such rapid and extreme changes. Radiation is another invisible but deadly threat. Space is permeated by solar radiation and cosmic rays, high-energy particles from the sun and beyond our solar system. An unprotected human in space would be exposed to levels of ionizing radiation that could damage DNA and increase cancer risks significantly. Additionally, solar particle events, or solar flares, can release massive amounts of radiation, potentially fatal in a short amount of time if proper shielding or protective measures aren't in place. Finally, the lack of breathable oxygen in space leads to asphyxiation. Human bodies, reliant on continuous oxygen supply, would be unable to survive the vacuum, resulting in hypoxia and loss of consciousness within seconds. The absence of air also means no sound transmission, adding to the eerie, isolated nature of space. The vacuum of space is a perilous environment where atmospheric pressure, temperature extremes, radiation exposure, and lack of oxygen each pose immediate and mortal threats to human life. These hazards underscore the critical importance of advanced spacesuits and life support systems, which are essential for any endeavor beyond Earth's protective atmosphere, underscoring how fragile and finely tuned human existence is to our planetary conditions. Long-term exposure to cosmic radiation presents significant hazards for astronauts, impacting their health and safety during extended missions in space. Cosmic radiation, primarily composed of high-energy particles from the Sun and beyond our solar system, poses unique challenges compared to radiation we encounter on Earth. Earth's atmosphere and magnetic field provide substantial shielding, but in the vacuum of space, astronauts are much more vulnerable. One of the principal dangers of cosmic radiation is its potential to cause acute radiation sickness during intense exposure, such as from solar particle events, SPEs. SPEs can flood the surrounding space environment with energetic protons, delivering radiation doses that can exceed safe limits in a matter of hours. Symptoms of acute radiation sickness include nausea, vomiting, fatigue, and, in severe cases, damage to bone marrow, leading to an increased risk of infections and hemorrhaging. Even in the absence of acute radiation events, the chronic exposure to lower levels of cosmic radiation over months or years, such as during missions to Mars or extended stays on the International Space Station, poses serious risks. Ionizing radiation can damage the DNA within cells, leading to mutations that may manifest as cancers later in life. Studies have shown that astronauts exhibit increased risks for various cancers, including leukemia, lung, and digestive system cancers, attributable to their exposure to cosmic radiation. Beyond cancer, cosmic radiation can also cause cardiovascular problems. Research suggests that radiation exposure may contribute to the hardening of arteries, atherosclerosis, and other cardiovascular conditions, which can significantly impact astronauts' health. Additionally, radiation can negatively affect the nervous system. Exposure to galactic cosmic rays, GCRs, has been linked to cognitive impairment, memory deficits, and increased risks of degenerative neurological diseases like Alzheimer's. These neurological effects could hamper an astronaut's ability to perform complex tasks, make decisions, and maintain overall operational efficiency. Long-term exposure to cosmic radiation also poses reproductive risks. For astronauts of reproductive age, radiation could affect fertility or cause genetic damage that might impact their offspring. Moreover, the immune system is not spared. Radiation exposure can weaken immune responses, making astronauts more susceptible to infections. Mitigating these dangers requires comprehensive protective measures, including advanced shielding on spacecraft, habitats, and within spacesuits. Additionally, medical protocols, such as pre-mission screenings and post-mission monitoring, are essential to manage and mitigate the long-term health effects. Pharmaceuticals that can protect cells from radiation damage, known as radioprotective agents, are also being investigated. The dangers of long-term exposure to cosmic radiation for astronauts are significant and multifaceted, affecting nearly every system in the body. Addressing these risks is critical for the success of long-duration space missions, shaping the future of human space exploration. A micrometeoroid puncturing a spacecraft represents a significant hazard, capable of initiating a cascade of catastrophic events. These tiny space debris, often no larger than a grain of sand, travel at extraordinarily high velocities, typically tens of thousands of miles per hour. At such speeds, even a small particle possesses immense kinetic energy, making it capable of penetrating spacecraft shielding and causing serious damage. When a micrometeoroid impacts a spacecraft, the immediate danger is the puncturing of the hull or critical systems. The spacecraft's outer structure, although designed to withstand some degree of impact with multi-layered materials such as Whipple shields, isn't impervious to all collisions. A successful breach of the hull would result in a rapid decompression of the spacecraft's interior, where the air pressure drops precipitously. For astronauts inside, this means a sudden loss of oxygen and exposure to the vacuum of space, leading to potentially fatal conditions within seconds if emergency measures aren't swiftly enacted. In the event of a puncture, the escaping air could cause any loose objects to become dangerous projectiles, further endangering the crew and sensitive equipment. Moreover, the sudden decompression can create a turbulent environment, disorienting crew members and complicating immediate response efforts. Astronauts would need to quickly don their spacesuits or move to a safe, sealed compartment to survive. Beyond immediate decompression hazards, micrometeoroid impacts can also damage critical spacecraft systems. Vital components such as power supplies, communication arrays, or propulsion units may be compromised. A puncture in the cooling system, for example, could lead to the overheating of electronic equipment, causing malfunctions or even fires. Damage to the power generation system, like solar panels, could cripple the spacecraft's energy supply, impairing life support systems and making it difficult to maintain a safe habitat. Thwarting a micrometeoroid's effect requires a well-thought-out response strategy. Spacecraft are designed with redundancy in mind, allowing alternative systems to take over if primary ones fail. Leak detection systems and automated sealing mechanisms play a crucial role in isolating punctured sections to minimize decompression risks. Crew training is equally vital, ensuring astronauts are prepared to quickly seal breaches using repair kits and pressure suits, securing their survival while they execute necessary repairs. The potential for a micrometeoroid to puncture a spacecraft serves as a stark reminder of the inherent risks associated with space travel. Despite technological advancements and safety protocols, the unpredictable nature of space debris demands constant vigilance and preparedness. The ability to swiftly and effectively respond to such an incident is crucial to ensuring the safety of the crew and the success of the mission in the perilous environment of space. The psychological effects of isolation in deep space pose significant challenges for astronauts, potentially impacting their mental health, emotional well-being, and overall mission performance. These challenges stem from the unique high-stress environment of space, extended periods away from Earth, and limited social interactions, all of which can exacerbate feelings of isolation and confinement. One of the most pronounced psychological effects is the phenomenon known as space adaptation syndrome, which includes a range of symptoms such as disorientation, stress, and anxiety. The lack of familiar environmental cues and the drastic difference from Earth's gravitational pull can lead to sensory conflicts, making it difficult for astronauts to adjust. During long-duration missions, these symptoms can evolve into more persistent issues, such as chronic stress and anxiety disorders. The isolation from family, friends, and the broader community can deepen feelings of loneliness, leading to depression and a decline in morale. Cognitive performance can also suffer due to isolation and confinement. Astronauts may experience difficulties with attention, memory, and complex decision-making tasks. The monotonous environment and repetitive nature of daily tasks contribute to cognitive fatigue, reducing efficiency and increasing the likelihood of errors. These cognitive impairments can be particularly dangerous in a high-stakes environment, where precise actions and quick thinking are often required to address unforeseen challenges or emergencies. Sleep disturbances are another common issue, exacerbated by the lack of a natural day-night cycle and the stress of the environment. Poor sleep quality and irregular sleep patterns can negatively affect mood and cognitive function, creating a vicious cycle that further undermines mental health. Moreover, the confined space in spacecraft can strain interpersonal relationships among crew members. Conflicts may arise from close quarters and limited privacy, potentially leading to interpersonal tensions. Effective communication skills and conflict resolution strategies are essential to maintaining a harmonious living and working environment. Teams must be well prepared to handle interpersonal conflicts constructively, ensuring that minor disagreements do not escalate into serious disputes that could jeopardize mission success. To mitigate these psychological effects, space agencies implement comprehensive training programs that include psychological preparedness and resilience training. Crew members are educated on recognizing and coping with stress, utilizing relaxation techniques, and fostering a supportive team dynamic. Regular communication with mission control and psychologists back on Earth provides additional support, offering a lifeline to mitigate feelings of isolation. Moreover, efforts are made to enhance the living environment in space. Personalized quarters, recreational activities, and virtual reality experiences that simulate familiar earthly environments can help alleviate the monotony. Scheduled leisure activities, exercise routines, and social interaction protocols are incorporated to maintain psychological well-being and physical health. The psychological effects of isolation in deep space are profound, potentially affecting cognitive functions, mental health, and interpersonal relationships. Addressing these challenges requires thorough preparation, ongoing support, and innovative strategies to create a supportive and stimulating living environment for astronauts, ensuring that they can perform their duties effectively and return safely to Earth. Imagine you're floating thousands of miles above Earth, surrounded by the vast vacuum of space. You rely entirely on complex equipment that must work without fail, day and night. Consider the International Space Station, ISS, orbiting roughly 250 miles above our planet at speeds of 17,000 miles per hour. If crucial systems like the oxygen generators, water purifiers, or thermal control units, they keep the station in livable conditions, were to malfunction, the consequences could be dire. In October 2006, for instance, the Electron oxygen generator on board the ISS failed, raising alarms and forcing the crew to quickly activate backup systems to maintain breathable air. But it's not just life support systems at risk. Equipment failures can affect navigation, power supply, and even communication with Earth. Take the infamous example of NASA's Mars Climate Orbiter. In 1999, a simple mix-up between metric units and imperial ones led to its untimely destruction upon entering Mars' atmosphere, burning up due to incorrect trajectory calculations. These instances highlight a poignant reality. In space, the margin for error is virtually non-existent. A single malfunction, whether due to human error, software glitches, or cosmic radiation, can spiral into catastrophic outcomes, jeopardizing missions and lives.